Good morning, good afternoon, SOC 100 crew. Good evening, wherever you might be. Welcome to another episode. Get your coffees ready. How's it going, everyone? How's the SOC 100 team doing? That's right, Chris. But I don't need to be motivating you all. Hopefully just the concept of what we're doing here. Debating enough. And some cool stuff. Just finished breakfast on time, KS. Yeah, same. I actually just finished up too before stream. Coffee ready, tea ready, water ready, everything to go now. New philosophy for upskilling in blue team. WWAD? What would Anthony do? Oh man. Controversial answer. On blue team side, what would Anthony do? I'd go to the red team. But that's just me. That's just me, because that's what I did. I didn't stay on the blue team. No. Blue team gets a little bit of hate sometimes. Also equally fun in its own ways. Different strokes for different folks, you know? Each their own. Thanks, Chris. Yeah, have fun with the recordings, man. We'll see you, December 1st, right? Like 2 weeks from now? Yeah, next Sunday. Sweet. CI. Yeah, have a good day, Chris. Hey, Hades. CI, how long did it take for you to upskill for red? Let's see. I think if you counted my GRC experience, both from technical and non-technical types of industries and roles, because I mean, I started back, this was 2015 when I stepped into like an executive type of operations slash GRC slash kind of risk management position. I think I've said this before, right? And then it kind of like, I got a lot of exposure to IT during that time. So technically from then, if you want to count it, but I would say like hard earned, I think 3 years, from 2018, no, 2 years, from 2018 to 2020. That's when I went like fully technical at that point, an analyst and engineer and IT manager positions. So 2 years from that point, and then I went fully onto the red team. And I was dabbling. I started to do my own pro bono consulting around that time, from like a year-ish in from 2018. So like unofficially, I guess like a year, and I started to just mess around and test the waters. And then more officially, I went full-time in 2020. Yeah, like the end of 2019, right before all the pandemic and everything, is when I went full-time pen testing, red team, and consulting. And then did that for a number of years before coming on to Level Effect over here. 2 years is pretty fast. Yeah. Yeah, I definitely know. My story won't be the same as everyone else's, for sure. Yeah. I definitely fast-tracked myself as much as I could and spent a lot of time studying and dedicating to this. And keep in mind, I grew up... I was introduced to computers at like 7 years old kind of thing. I was messing around on DOS. I was trying to get a really bad modem connection on Windows 95 and up. to play games online. I was messing around building computers myself when I was like 13, 14. So keep in mind, I had a lot of like early life experience around all this stuff as well. So I don't compare. And again, this kind of goes back to what I said to you and everyone else too before, CI, is you can't compare yourself to other people. You have to just look at yourself. You really have to look at yourself and say, like, what are you willing to do? What are you willing to overcome? What are you willing to dedicate yourself to? And that's really what will determine and dictate sort of like your time and success of getting to whatever you want to do in life. It's not just IT and cybersecurity as well. So KS, that's your entire professional experience. I think with the right environment, anyone can, yeah, oh yeah, like I say that, like, and I think you can all see we're about what 40 to 50 hours in of live training. As you are layering on this knowledge, like, this isn't, to say like a cliche statement, this isn't rocket science. It's just a lot of exposure to how to use the technology and just understanding terms and definitions. That's really it, like, for the good portion of getting started in IT or cybersecurity. It's just like, how much knowledge can you get inside there and retain it? So there's a lot of studying, a lot of practicing, a lot of output, input, output. That's really what it is. So how much time you put into it and how effective you are with your time is going to determine your results. So if you have the right recipe and you're willing to put the work in, you'll get there. You'll get there pretty quick. If you dabble around, and I think that's one of the key reasons why we made SOC 100, is because a lot of students were coming to us who had they were like just completely stuck in tutorial land for like years. They would take just a constant slew of entry-level courses over and over and over again from different providers and different vendors and platforms, and just like in circles, just like constantly doing that. Whereas you can see with the SOC 100 course, it is pushing you along. There's like a flow, there's a stream. We've started, it's November 17th. We started this like a month-ish ago, like a little over a month. And we literally went from the desktop of Windows, just opening up an application, to now we're going to be doing network and malware traffic analysis. So it's a stream that it's going to be a little uncomfortable at times, but it's pushing you, and it'll continue to push you all the way. Yeah. Yeah, exactly. Like KS. What worked for you hit the ground exactly. So you started to output right away, and that's what I encourage on the other streams as well too. Similarly to you is kind of what I did, KS. Like, as soon as I felt productive with what I learned, I immediately went to the IT department and I said, "Tell me when you're doing your next server installation." And I wasn't in IT at the time. I was still in that like GRC ops manager type of role. And I said, "Just show me when you're doing the next server installation. I want to show up." And I did. And I just shadowed. I just watched, and I said, okay, you just did that on the server screen. What did you do? Now let me try the next thing. And that's what I did. Like, as soon as I felt somewhat comfortable, I just started to apply myself as much as I could. If you keep on overloading yourself with knowledge, the human brain can't retain that much. So it's going to start forgetting things, and you're just going to start layering in new knowledge. And you see, like, there's a bit of a vicious cycle there. So you keep trying to get yourself to apply and put output, but you've already started to forget what you learned. So it's kind of like this cycle of like input, output, and you have to keep a rhythm. Now, some people can input a lot and then output a lot. Some people can input a little, and vice versa. Everyone's got their own different type of ability. The frequency is faster, but you need to start applying yourself. And you're going to see now in, what is it? On December 1st, we're already going to be doing the portfolio. We're going to be doing the career prep with Chris, who's just in the chat over there. And the expectation is every single SOC 100-1 student must either build out a full home lab on their own, and we're going to give you the steps, and you're learning how to do this effectively, or you're going to build out like whatever you can. Like virtualize one machine at a time on your home computer. But the expectation is every single student must be able to build their own home lab and start applying these things on their own. And we are going to show you the steps to get there. And if you can do that, that's effectively kind of like what KS did. That's what I did. That's what everyone who, at least everyone that I know that really jumped into IT and cybersecurity from a different career or just not from it at all, the people that really started to apply themselves right away got into the career very quickly or much faster than a lot of people that just got stuck in tutorial land constantly with input. Kind of like struggling for years, like I can't get in, I can't break in, and then you look at their experience and they just have like every cert possible and every course possible, but they haven't been able to produce anything. So that's something to think about. That's my morning coffee rant for it right there. Right, so yeah, get the coffee in you. Good call. I hope that helps everyone listening too. I think we got a little over 20 people inside the stream right now. Yeah, KS, so that's funny because being able to build a lab was a requirement to be... exactly. My first technical position, like fully technical, the job interview was a take-home assessment where I had a weekend to put together a small enterprise network. They gave me all the connections, like remote in, and I had to configure it myself and then say that I did it and kind of walk them through it. That was my first interview. And I did it. And I got the job for it. I didn't have like technical experience at that time, but I learned how to do that stuff so that when they gave me an actual technical take home, I could do it. I could demonstrate it. Same thing. Zeno's asking, what's a fair entry salary these days? That is... I think you need more variables on that question. Like, Canadian salary, it's much lower than a US salary, for example. So, like, location, state maybe, country, and target position as well, too. I think if you can define that criteria, then you can probably get a different answer. Yeah. We are on we're on day 11, wow. Day 11, Wireshark. Oh, what's this? Set up. Our doubles say, no disrespect to anyone going that route, but I see a lot of people with the WGU degrees in that situation. Yep, exactly. It's exactly what I was saying to you. It's awesome to check a box, but many I see still can't get a job because they have no practical experience, just a bunch of certs. Exactly. It's the same thing, yeah. Now, a degree is... you have to look at, like, what's the objective of what you're doing there, right? A degree is good on paper for a requirement and like a check in the box. So like that's how you should be looking at it. And then ideally you pick a degree that can help you with as much practical experience as possible as well. That's kind of like your ideal situation right there. But don't kid yourself. Like don't go and get a degree or a cert and be like, hey, where's my job? Because that's like saying you're looking for like a plumber to come to your home, like you have a leak, you got a problem. And the plumber's like, hey, I study this book. I know what to do. Are you going to hire that plumber to do the job at your home? Maybe that plumber read like 15 books, and then are you going to hire them, or are you going to hire the plumber who's never read anything and has like a portfolio of pictures? Of like, hey, like I went to this client's house, I did this, I did that, I did this. These people can vouch for me, but I don't have any certs. Hades, yeah, that's why I always say do it yourself, fail, and do it again, 100%. Kim, salary in Switzerland is also generally higher. Yeah, that too. It's really going to start depending where you're looking at. Sadly, a lot of people think cert equals job. So like KS, you know, like to be fair, like I think that was there was a bit of a market problem that happened during the pandemic where it was just like blasted everywhere of go get your Security Plus, take a boot camp, and you will get a job. And I've said this on other streams, and I'll always say it. That really painted a strong misconception of the reality of starting in IT, and like not just cybersecurity, but it's starting in IT. That really painted a big misconception. And the market has corrected itself now where that is really no longer a viable option. But there's still a lot of buzz of, and there are a lot of courses and a lot of boot camps that were designed around the Security Plus. So they're still going to promote it. So, you know, like we're seeing it level off, but it's still going to take a little bit more time before that really corrects itself on the training side and the general area of communication. I've also said before, like 2 years ago, you would never hear like influencers and Redditors and the general messaging wasn't really around of like cybersecurity is not entry level. I saw a lot of LinkedIn posts of people going on there of like, you have to give entry level cybersecurity applicants a chance that have no experience and no certs really. Anyone can do it. And like it was being promoted, and the people that would come on and be like, hey, wait a minute, like chill out, go get your IT experience, like go and start with the basics, we're getting completely blasted. And those people stopped saying that. However, now you actually see that as a general message. It has sort of worked itself out, but there was a time, like God forbid, that you would ever say cybersecurity is not entry level. Like you didn't even hear that. It wasn't a thing. A lot of us that were in the field were trying to explain that, but the message was really hard to get out. So that's an interesting thing that happened in this industry for sure. So Demorier, yeah, you're Sir 43 currently and been working tech for the last 7 years. All that time without any qualifications at all. Exactly. And yeah, you don't need to finish school. There was this strong push, especially like I remember growing up to, and like if you didn't finish high school, like you were a failure. If you didn't finish college, university, like you were a failure, kind of thing. It was so frowned upon. Like you had to just go through the mill. I never liked that idea back then. I never did. I went to a college over here afterwards, and I didn't want to. I wanted to just go and do my own thing. I wanted to like teach myself and fly at home and read books and stuff. And I think that's kind of what you're saying. Is like you got jobs from self-taught knowledge and skills you picked up working with computers, and that's exactly it. Like if you can sit at your desk and tinker around with your computer and you enjoy that, like you enjoy messing around with it, and it's fun, it's interesting, it's intriguing, and you want to know how it works, and you want to get it to do things and improve some type of like life thing, right? Like that's what a computer can do. It can automate and do things very quickly. Like stuff like that. Or maybe you're just a gamer. Maybe you like networking. Maybe you like data and signals and stuff. And that's what I've seen now in the past 5 years almost now of training, is that those students that were like that, like I went to a B-Sides conference over here in the West Coast a couple years back, and I remember like the keynote speaker, he went up and he was just like, if you are a gamer, I will hire you. If you are an accountant, I will hire you. That's how he opened it up. And he was trying to explain that when you're in that type of position, like if you're looking at someone who's in accounting, right, you're just looking at a lot of financial outliers and anomalies. And that mindset, if you can find someone who has that and then they also like cybersecurity, they're going to do so well. Because that's what cybersecurity is. You're looking for outliers and anomalies just with different types of data sets. So that's a win. He also talked about like gamers typically do quite well in cybersecurity as well, because like especially RTS, like real-time strategy and turn-based strategy is what he was talking about. Not like COD, but rather like gamers that are really interested in like civilization, games that require you like that 4X kind of strategy with like economy, warfare, politics, trade, and such. That requires you to really manage a lot of different types of resources and currencies and different things and kind of stack them together in priority and what's necessary. And that's a very strong skill set to apply to cybersecurity as well. Yeah, Age of Empires. Yeah. Yeah. Exactly. Like, and so if you can find someone like that who also likes tech and cybersecurity, those are strong indicators that they're going to do very well. So it's an interesting career and an area of tech, cybersecurity for sure, because of those notions. So yeah, I fully agree with you, Demorier. Fully agree. My experience that got me employed and successful in this field came from a lot of like troubleshooting, installing like old video cards back then, troubleshooting Windows, networking issues. I was troubleshooting DNS and like IP issues when I was 13. So like it wasn't foreign to me when I started to study it later. That was actually better experience for me, honestly. Like my home network issues was better experience than like I was trying to figure out like these courses at the time when I was trying to transition fully into cybersecurity. That was more experienced. R-Double saying, nice, you're an inspiration. Demorier, yeah. Yeah, I hope Demorier is a good inspiration for you, R-Double, and others in the chat as well, too. I agree. It's about putting the work in. It's not about slapping certs and theoretical knowledge on your name. I heard someone once say that's the equivalent of being what did he say? A paper tiger. And I thought that was like the best way to think about it. Paper tigers. Like imagine a tiger jumping at you, but it's made out of paper. What's going to happen? So, interesting stuff. Good conversation. It's a good topic to get into. But enough of that. Unless anyone else has any other questions or comments on that type of notion. Otherwise, we can jump right into where we left off. I'll give a second there for chat. Any comments anyone might be typed up. Otherwise, we'll kick it off. Okay, no questions, no comments. Get started. Set up. Cool, let's fire up our systems. We just need the Windows one for now. So no need to fire everything up, save your credits. Just the Windows workstation. We're going to fire up Wireshark. Back into it. Wireshark. Yeah, there you go. All right. Let's have some fun on that. Not Baby Shark, but Wireshark. Pew, so you're asking, do you think it would be hard to pivot from digital media, motion graphics, video into IT? I'm looking at getting into a second bachelor's to make a change. I have a lot of skills in Python from animating with it in Blender and Unreal Engine 5. So your last statement there, I think you are already ahead of a lot of the people starting and trying to get into this field, just by that alone. We had a student in the past. It was similar. He was in 3DFX though. And he studied, I know he went through our training a couple years back. I think he was studying like more officially for like 6 to 7 months, and then he got into the field. He grinded really hard though. I think he was putting in like 40 to 60 hours a week of studying. But his background was kind of similar to yours, and he got in just fine. Your experience with Python is going to help you a ton, by the way. So, yeah, you can definitely do it. If you're willing to put the work in, totally, with that experience. Also, welcome to the chat, Pew. It's the first time chatter over here. To the stream and the crew. Alrighty. Let's see, the system is loaded. Wireshark. Wireshark time. We're going to take a look at the 3-way handshake. Yeah, you like that, KS? Thought that'd be pretty fun. Wireshark, to-do. Yeah. So we're 31 minutes in. Just gonna get things started off over here and do like a small break for some coffee and such. Screen set up though. It's flying around everywhere. Cool. All right. So yesterday we took a look at Wireshark. Wireshark. So what is Wireshark again? Just a quick refresher. And Wireshark is essentially a network protocol analyzer. That's what it is. And it helps us visualize network traffic in a way that we can get a high-level picture of what's going on in a GUI type of view, and allows us to apply filters on the network traffic metadata that we're seeing. And the metadata being like the source IP, source port, destination IP, destination port, etc., stuff like that, the URL, all those things. Anything that could be like a unit of data, Wireshark will be able to visualize for us that in this packet-like view, and then we can filter through it to get a bit of an understanding of what's actually happening instead of just looking at text and models and flowcharts. Also great for analysis, great for forensics, and what we are going to do, as said in chat yesterday, is we're going to bring all of this, we're going to bring these packets to life. That's what Wireshark is going to do for us. That's what we're going to focus on. So we're going to start off today, we're going to be looking at the 3-way handshake. We've talked about this. We've talked about a TCP connection previously. We walked through the process and the flow of what actually happens. We talked about this, the TCP flags that are set, but we haven't actually seen it happen in action. So that's what we're going to do today, at least to get started. We're going to do an analysis and look at what this looks like. So inside of your VMs, you're going to find your lab data. We'll go to local disk C, and we're going to go to the Foundation's lab data folder, and we're going to look for a network traffic analysis. So what we want to look at is the HTTP analysis PCAP, I believe. Make sure, yeah, we're tracking that one. Cool. So HTTP analysis. So it should open up pretty promptly. There should be a total of 33 packets inside here. So let's get started. first things first, a little reminder on the client-server model. Remember that everything in networking operates on a client-to-server model. That means the client makes a request to the server, server sends a response back to the client. That's the client-server model. And just about everything in networking operates in that manner. There is a one-to-one connection to something. The exceptions being some things like the ARP protocol that we saw yesterday, that is like a broadcast type of address or a broadcast connection. And there's also a multicast type of connection, which we covered a little bit on the class A, B, C, D, and E private address range. Some protocols also provided too, and multicast being one to many, not one to all. So it's sort of like a selected group that you would broadcast to. But even in that stage, it's still a client to a server, but client to servers. So there's always this notion of request, response, request, response. None of this is a dynamic connection that is happening all the time. It's more so static, like transmit, receive, kind of like talking on a radio. And I really want to get that message across as a reminder and refresher, because you're going to see that in action here. And that's where a lot of vulnerabilities occur as a result. Cool. So we're going to start off, and I think we're going to look at packets 1 and 2. So we're going to start performing a little bit of a DNS analysis over here. And we've talked a little bit about the DNS request process. So let's see what's actually happening in this case. Now, yesterday I added in some columns. So I added like source port, destination port, and some other things like MAC addresses inside here. So my view is going to look a little bit different if this is your first time hopping into it. And as a reminder, you can always go inside of different headers and you can grab these fields. You can right click them and you can add them to a column for us to see up above. Or you could go and remove them entirely. We probably don't need the MAC addresses in this case. So get rid of some of that layer 2 information. So let's take a look at packet 1. Packet 1 here, we have the DNS protocol in action. We have source IP. And it actually, is this clear? Like, do you need me to zoom in a little bit? Let's do that. Probably a little too small. Looking on my stream screen. That might be better, yeah? Is that better? Or is that just like too big? Let me know, please. Cool. Good stuff. Alrighty. Good stuff. Cool. Okay, so first request going on over here. Packet 1, we have a source IP address of 1020.8.14. It's going to a destination of 10.10.0.2. Let's kind of walk through some of these layers over here. Again, first layer of the OSI model, this is all the Ethernet information. Largely, for the most part, we can just start skipping everything related to what's actually happening on the wire. Not super helpful for us because we're not physically inspecting or working with the network. A lot of this is virtualized. Still interesting to take a look at as you start getting familiar with like what this actually does appear as. But let's take a look over here. And at layer 2, we're kind of looking at some of the MAC address information. So here is, again, if we were inside of a switch-based network, layer 2, without having to route by IP, then we could look at some of this information here of source MAC, destination MAC, of what's actually being requested here. But we're not going to look too much inside of that. What we want to look at is more so the DNS, so the domain name system header. And this is actually going to give it a little bit more life and feeling of what's actually happening here. So let's walk through it. Inside of these headers that are represented by this hexadecimal value over here on the bottom right pane. Actually, this is a little bit too big. 1 second. Is it getting cut off? Okay, that's better. There we go. Perfect. Okay, so we can see that there are actually flags. And you've seen like on the command line, right? We have flags, options being given to commands for them to be able to do different things. Very similar. This is a general concept when it comes to computing, is we have flags that are set up to change the operation of a single request or a single command. This saves us the time of having to program and create so many different variations just by having these switches to do different things with it. So you'll see this a lot inside of protocols as well. So in this case, we have a couple different flags going on. We have some requests of what we're trying to set with this DNS request. You can see that the recursion is desired. So this is where we talked about that recursive DNS lookup, where we're going to make a request out to the first DNS server that is available to us. It's either going to be, remember, our local cache in this case, which has been bypassed, so this is now going over the wire. And this is going to hit our router maybe if it stores DNS information. Or it's going to connect to our ISP servers that might have a DNS server provided for us with recursive lookup. And remember, recursive DNS is looking within itself, kind of like going through itself first and then completing before going to the next server. So we can see that this DNS request has been set up with recursion desired. We want to perform a recursive DNS lookup, and this is how the DNS server receives this request and is able to interpret it, that this bit has been set, has been flagged. So you can actually see this stuff happening. You don't have to question yourself anymore. Like, why is this happening in the model? Well, you can take a look at it from the network traffic perspective itself. You can actually see how the server knows that this should be a recursive DNS lookup. So that's pretty cool. Next, we have this queries field. And this is actually the domain. So this is what the user typed inside of their browser. They want to go to demo.redmine.org. Now, this query is naturally going to be asking for a type A type of request. We're not communicating over IPv6. We're trying to communicate over IPv4. So we're actually requesting a DNS type A record. Remember the DNS records? So we're trying to get that A record, and we can see that it's requesting like a domain. And we're trying to get the IP address here. So that's what's happening in the first packet. Type A, we want the host address of demo.redmine.org. Now it's going to hit the gateway, and in this case, this is going to be the router. We don't see the rest of that communication though. Now that whole DNS lookup process happens. It's going to hit the root DNS server. It's going to hit the next set of DNS servers. This could be maybe the subdomain, further layers of DNS servers in action, and eventually it's going to try to hit the authoritative DNS server for redmine.org. And then from there, ideally, we should get the information. So it's going to hit the .org DNS server and then look for anything that's Redmine from the next server, and that's going to send it to the authoritative server for redmine.org. So that company, it's either their own server or they have it registered through like another company, and they're storing space and storing DNS information over there. Either one. Finally, that server is then going to send the information back to our router, and then we're going to see the response. So this is the response happening right now, coming back to us. So our router has now obtained that information. And the cool thing about Wireshark is if we have DNS expanded here as a header on this packet details pane in the bottom left, when we click on the next packet, it's still going to be expanded. So we can have like a, I guess like a chronological type of inspection happening here. Like we're inspecting DNS here, inspecting DNS there. And it's more specific and explicit for what we're trying to achieve, as opposed to, imagine if I went from here and I'd have to always expand headers. Well, the nice thing is that it actually knows what we left on the last as like a history. That's pretty cool. So here's the response. So you can see standard query, demo.redmine.org, standard query response. Here's the A record, demo.redmine.org, and the IP address is 46.4.36.71. Take a look at these DNS flags now being set. This is a response. Recursion was desired, recursion is available. So it was able to perform a recursive DNS lookup. That's pretty cool, right? Like we can see that actually happening now in motion. As opposed to us, again, guessing on previous models, you can physically see the bits being set to tell you exactly what the DNS request was desired, and that recursive DNS was actually available. Now, if recursive DNS was not available, we would see a 0 over here. So let's see the actual response that's been given back to us. And the response is demo.redmine.org, type A. Sorry, we're still in the query. I have to go into the answers. So look at the answers. And let's scroll down over here. And the answer, we have demo.redmine.org, type A. And our address has been provided to us. 46.4.36.71. Name, demo.redmine.org, type A record. Super cool. That's a DNS request happening on the network. Does that make sense? Isn't that a lot easier to look at now? Yeah. That's right, Joe. Hot garbage, yeah. Pews, why not do both? Yeah, that's true. Why not do both? If you have the time and bandwidth. Does anyone have any questions on that? Like, is that, I guess, is that clear enough? That is actually a DNS query and response happening over the wire. This is how we now have the IP address. It's been given to us. And you can see that, well, what is the next packet? The next packet is the HTTP request with that IP that was given to us of 46.4.36.71. Any questions on all that? Always the Sundays. Everyone's always quieter on the Sundays. Every time. Everyone's more like in lurk mode and stuff. Okay. All right. Well, I hope that's clear. It seems clear enough. I'm taking in, but it's great to see this in real life. Yeah, cool. Yeah, it's great to actually see it. No question for you. Low battery Sundays. Yeah. Yeah, it's Sundays, right? People want to kind of chill out a little bit. But, cool. How long do you think it will take to really get to a point where we can leave Wireshark? Come back to it and remember what we're looking at. Man, pretty loaded question, because I don't know your baseline. How long do you think it will be to really take to a point? I assume 0? I mean, if you've been following along just from SOC 100 from the beginning, and you're up to this point right now, you should, after this stream, be able to go and reproduce this. Like, you should be able to open back up Wireshark and look for these types of protocols on your home network or other PCAPs. You should. We've walked through the process flowchart many times. Many times at this point of like what's going on. So it's just a matter of like find out where it's not sticking for you and sort of identify that little thing. But you should be able to look at it right away. This is just the beginning. We have a lot more PCAP action to look at today and next Saturday. I think it's probably like what? There's probably like 10 hours of looking at this stuff. That's a lot of time. Hot garbage Wireshark might be a perishable skill. Why do you think that? Yeah, Demorier. Agreed, exactly. That's what KS and I were kind of talking about earlier in the stream, and what you were highlighting too is don't just follow my labs. Don't just follow what I'm saying and taking your notes. You need to go and apply this stuff. Why do you think in the Linux module, the challenge is go use Linux for a week? That's the challenge. Just use Linux for a week. Wait until you see some of the networking challenges that I'm going to throw in. There's some, but I'm going to throw in another one. Yeah, hot garbage. I'd like to know, why do you think that Wireshark might be a perishable skill? It's a tool and it changes over time. So, yeah, I want to highlight something you're saying that I hope people can understand as well. I don't want you to master Wireshark. I don't want you to be like, I need to become the Wireshark pro. That's not the point. If you understand how the network protocols work and what to look for, then it doesn't matter what tool you use. You just need to know how to use that tool to get the results of looking at those protocols in action. Wireshark is helping us get a visualization of what's in front of us at a better view instead of just doing models, flowcharts, and analysis of text. It's a very powerful tool for that. Things change in the tool. Updates are made. I want you to be thinking in your head, if I were to use Wireshark, where would I find the DNS query for an A record of example domain? And if you can think about it like that, then it doesn't matter what network analysis or protocol traffic analysis, it's whether it's on the command line, whether it's Wireshark, whether it's T-Shark, whether it's Zeek, it doesn't matter. It really doesn't matter. If you can think about it like that, then you just need to find out how to do that lookup in that tool to be effective. So yes, Wireshark, I wouldn't even consider a skill. So I don't even actually consider it to be a perishable skill because it's not like that. That's like saying you want to be really good with using a screwdriver. Why? Right? Why? You might need a power tool. You might need an automatic screwdriver. You might need different types of screwdriver bits. You might need a hammer. You might not even need any of those. If the desire in that case is to bind two materials together. So hot garbage, yes, foundational skill is more important than being a guru. I would say largely yes, just it also kind of depends. Like if you want to become the Wireshark guru so that you can be like a teacher and a trainer on it, there are certifications for it. Of course there are. Wireshark training. So you could go deep. There is training available for this. Wireshark University. And there is SharkFest that you can go to. You can become the guru if you want to be. If you want to become the super Wireshark guru, which it can do a lot of awesome stuff. Like, it is great for network forensics. It is great for network protocol analysis. It is amazing. By all means, if that's what you want to do and you want to become a network engineer, you want to become a network architect, Wireshark's going to be a pretty powerful tool to keep in your belt with a lot of features to help you get there. But yes, don't become reliant on it. Joe M 2806, understand that the DNS query uses UDP or TCP. It uses UDP. On this instance, I see UDP was used, yes, because DNS is a UDP protocol. TCP is used, which we're going to look at shortly after this, actually, when we want to make a session-based connection, meaning that there is a sequence of events like 1, 2, and 3 that have to occur at a certain time. That creates a lot of overhead and bandwidth to create that TCP connection, which is called the three-way handshake, and we're going to look at that very shortly, actually. DNS doesn't care about that. DNS is just like, I just need to know the answer to my request. That is it. So you send it's a UDP type of packet. I send a request, send me the response whenever, I don't care, because there isn't a session. There isn't an ongoing connection that has to happen. KS is saying you can't build furniture only using a saw. You need to know how to prep the wood, install hardware. Exactly. Kim Fried, if you know the basics like using the right bit and pressure, you can use any kind of screwdriver. Exactly. At Level Effect, you will never hear us telling you that you need to become like a master of some tool. We don't even really advertise. You might go to some training providers and they're going to blast you like, oh, we're going to use all these tools. We don't care about that. We want you to understand fundamentally what's happening so you can use any tool. We want you to be tool agnostic. We want you to be able to hop in one tool 1 week, start at another company maybe down the road and use whatever their tool set is. We want you to use the right tool for the right job as needed based on the understanding that you understand fundamentally what you're looking for. That's how we do our training. That's what SOC 100 is about too. Taster, thanks for the follow. So this is good. Good questions. Coffee's starting to kick in. I think it's actually a bit of a coffee break as well. Steven's saying, I don't think it's possible to know or remember everything. No, it's not. It's not. That's why you need to fundamentally and conceptually remember everything. Yeah, it's second coffee time over here. Jixel, thanks for the follow. Let's take a bit of a break here. Try to do a break every hour. Do I use creamer? Absolutely not. I like my coffee like I like my metal. Black. I'm just kidding. That's from an old show. No, but I drink black coffee. Google to refresh your memory? Exactly. Yeah. Good. The more we can get the message across that you just need to generally understand things, you'll be fine. You'll be fine. Cool. Let's take a break. Let's take a break, and we're going to come back and look at the three-way handshake together. What we're going to do. So we looked at DNS. Now we're going to figure out first an HTTP request, which is super important. Super, super important. Yeah. Cool. Good. Nice. So what is your desk setup as for excellent workflow for being a remote SOC analyst? Like my actual desk setup? Well, I'm not a remote SOC analyst. I used to be a SOC analyst. Well, more like it was like an IT security analyst kind of in one. But that wasn't remote. My remote desk, I prefer... Okay, everyone's got their flavor. But sit stand, 2 to 3 monitors, clean, and then get it covered in cups and stuff by the end of the day and clean it again. Finax, you're a real big fan of these kind of streams, talking about the mindset and non-tech skills need to be... Oh yeah, totally. Cybersecurity and tech Soft skills are all skills. It's for every career. Okay? Ultra-wide monitor for me. I tried, man. I tried. I had the 49-inch, but it was too much monitor. Like, programs were always all over the place. Games never ran properly. I was just like, you know what? I just want a 27, 24, and a laptop. Like, that's good for me. I like to just be kind of focused. Now on streams, I use a 32 because I need a little bit more space all in one pane when I'm teaching and talking. And I look at a bunch of things. But yeah, I think 32 is pretty good. Demore is too ultra wides and horizontal, too wide and vertical. Yeah, just covered in screens. Yeah. You got to find what fits for you. I know some people that just have a single 27-inch or just have a single 24-inch. That's fine. Whatever's good for you. Some people like Vision Pro. Some people just want to put on the ski goggles and work inside of that. That's cool too. However you prefer. But cool. Let's go get some coffee. Okay? Go fuel up. We got some more stuff to dig into. And go into it from there. So, let's take a break. And as always, only ads on the breaks so that we're not getting in the way of the content. Okay, let's go. Let's be right back. Okay. All right, we're back. We're back. We're going to come back a little bit earlier, actually. Cool. Get to it. All right, up next, and welcome back, everyone, as well. Pin the message. Set it for like 7 minutes. It's too long. Okay. So, Karina, you're still peering into a 14-inch laptop, an iPad? Honestly, totally fine. It's a little tiny, but it's totally fine for now. Like, we're just kind of looking at a couple different things. I think at a minimum, though, you probably want to move that to like maybe like a 24-inch, just something a little bit bigger. But 2 screens are always helpful. CI, this is the 3-way handshake and client server model lab. And we are looking at the HTTP plus analysis PCAP. Cool. Okay, well, let's jump into the HTTP protocol request here happening. So we've now made a DNS query. We had a DNS response. We received our A record. We have our IP address. The next stage in this traffic, we can see that the client at 10.20.8.14 is now making an HTTP GET request for the IP address that we just received from the DNS A record. We can see that the destination IP address is now 46.4.36.71, and like we saw yesterday, destination port is port 80. And here you go. Here's the source port, that ephemeral port in action. So it was just grabbed at a random ephemeral port address as a source port because we don't care about that. But our destination port needs to be 80 to match up with the HTTP protocol. So let's see what this actually looks like inside of the traffic here. So first of all, something important to highlight is on packets 3 to 6, you can actually see a link, sort of like a little rectangle here on the left-hand side. Okay? That is suggesting that these packets are actually linked together. Okay. So what's happening here? Packet 3, we can actually see a GET request, like I said, and it looked like on the command line when we did that netcat get /HTTP, and here's the protocol, which we can see here on the right-hand pane, sort of like the breakdown. This is the hexadecimal representation, sort of like you can see these things, and they're formatted into these headers. So it performed an HTTP request, a GET request. That means like get the first resource at the root directory of the web server, which in this case is typically going to be like a web page, like that index.html. So you can see the request URI, and you can see the host. The host header contains what we put inside of our URL address bar. So sort of like demo.redmine.org. That's the host header that we want to request. And then there's a variety of additional HTTP headers that we're going to look at a little bit more like later and in depth. And there are a lot. Take a look at this. It's kind of a long list, but actually, how many? How many HTTP headers are there? I don't know. And for some reason, it's not even telling me the summary. But a lot. A couple dozen, maybe it looks like. All of these options here, effectively, that's what they are. They're kind of like options that you can add to your HTTP request to change the type of what you're looking for. So like in this case, we can see like connection is keep alive. So we can go and look up documentation. So keep alive. And close. So we actually have only two options here for the connection header. So again, indicates that the client would like to keep the connection open. So the HTTP protocol has its own structured way of formatting data on the request itself. And you use that with HTTP headers. And you say something like get root directory, host is the domain name, connection, I would like to keep this alive, etc. And then we have a really interesting header over here that we're going to spend a little bit more time on, and this is our user agent header. So, go back to that as well. And I want you to get a little bit comfortable looking things up as well. Obviously, we're going to explain things as we go, but I want you to start getting more now into that mode of documentation lookups. So the user agent, in short form, is just telling the server characteristics about your technology, like what you are able to support. Your operating system, browser, version, etc. It's telling us like, hey, we're on Chrome. We're using Firefox. We're on Mac OS, and we have the Safari browser, etc. And it's doing this because all of those browsers have very strict ways of working with different things, different types of data like HTML to render the web page and make you visually see it inside of your browser. The server has to know what your browser is and your operating system, etc., to send you the right resources. Now, all of this is managed by web developers. This is what they do. This is their specialty. You just need to understand in IT and cybersecurity the user agent characteristics of maybe the operating system. So we can see here, like it's Windows NT. So this is Windows 10, 64-bit. And it looks like they're supporting, so yeah, Mozilla 5, Windows NT, 64, Apple WebKit. So there's a number of different types of browsers that this user agent can support over here. Pretty cool. So that's effectively, like at a quick high level, what we're looking at when we see HTTP requests coming in. Now, let's take a look at the next request here. So it says get IP address over here. And now there's a bit of a continuation. And the server has now responded back to the client. And it's still under the hypertext transfer protocol. You can see there's a bunch of data over here. So data has been exchanged back to the client. And the client is now requesting the account register page. Now what we could do is we could actually go and right-click any one of these inside of the sequencer here of packets 3 to 6. We could right-click that and say follow, and we could follow the TCP stream or the HTTP stream in this case. We could see like what does this actually look like? Like what is the entire conversation? I'll kind of do that both ways just to show you. So in this case, you can actually see like the GET request, and you can go here in the bottom left, you can choose if you just want to see like the client to server or server to client in this case. So we can see the server's response, we could see the client to the server, what they requested, or you can actually see the whole flow of the conversation, depending on the view that you're looking for. And this kind of gives you like a high level overview of what's actually happening. Now, for whatever reason, we can see this actually, there was some type of error, like there was a problem with the request. So it says TCP previous segment not captured. So we actually ran into an error. And this is actually, like, it's kind of common. You're going to see the things like just, they get out of sequence, they get out of order, and packets drop. That's actually normal. Like, it's small, but it's normal. And it will happen, especially if you have, for some of those of you that have like 50 tabs open, we've all done it. Some of those have like 50 tabs open, or your network is congested and it's slow. Everyone's streaming Netflix at home and everything's just slow. People are downloading things. This is where you're going to start running into more of those issues. So Karina's asking, so is the following stream showing multiple packets? Yes. Yes, it is. The stream will show what's happening between packets 3 to 6 in a snapshot all at once. And it doesn't care about the other layers. It's only showing you the HTTP or the TCP stream, which is just a summary of the different headers. So if we wanted to see the HTTP stream of packets 3 to 6, we could follow that to kind of get a better human visual read. Like, this is easier to read instead of looking at the packets themselves. And you can just see the HTTP requests happening in action. Now, if we close that little X at the top right and we right click this again and we follow the TCP stream, you can see a little bit more, and you can see the entire session coming back both ways. That's pretty cool. So it looks like they tried to perform a GET request to account and register and ran into an error. Now, what they did immediately after was they performed a POST request. So it's a little bit different. Now, the POST request, the account register is sort of like going to demo.redmine.org, and what was it over there? Account register. Okay, so it would look like account register. So that's kind of what the requests look like here at the top. So you can see, like, it doesn't always include the demo.redmine anymore. That much is already implied. And we know that because the host header. And what we're trying to find actually is the URI. Now, we talked about this a little bit earlier. And I can't remember who asked inside the chat. They're asking like what are those things after the URL? So let's look at that again. My domain name. Someone's got to have a better model of this. Come on. Okay, yeah, I guess for all intents and purposes, this kind of sort of demonstrates it. Why do we get different results for TCP versus HTTP streams? So that's what I was trying to highlight over there, actually. So Finek, if you look at Wireshark, so let's look at that again. Remember in the bottom left, the packet details pane? These are headers. Headers of different layers and different protocols. So if I were to say, I want to follow just one type of protocol stream, well, that's effectively what it's going to do. So if I were to say follow TCP stream, well, it's going to follow the transport layer. It's also going to follow the rest of the layers after that. But if I follow just the HTTP stream, I'm only going to see the HTTP activity. And remember, HTTP this is better. Here we go. Yeah, okay, cool. So take a look at this. Yeah, makes more sense, right? So Wireshark operates the same way. If I say follow HTTP stream, then I am just going to get the layer 7 data and up. But if I say follow TCP stream, then I'm going to get TCP included all the way. all the way to the top. Remember, this is sort of like a layered view. And HTTP is a layer 7 protocol all the way at the top. It's not going to capture anything else before that if it's just the HTTP header. So going back to Wireshark, TCP, if I follow that, is going to pull everything from HTTP and up. Just in the case, like, if I were to go back to here and say follow, if this had the ability, it's not built in, but if I had the ability to say follow frame stream, then it would pull everything. But we don't need to look at all that information. We're really most of the time just looking at things from like transport and up. TCPs, flag settings, and different like layer 7 protocols and such, kind of like what we're seeing here. Cool. Yeah, so it makes more sense now. Yeah, good. Karina, were you thinking that too? Like, why is there a difference? Well, now you know. And knowing's half the battle. So let's take a look at the next request. So it looks like they ran into an error, and it appears that the account register actually was, it looks like it needed a post request. Yeah, thanks, Karina. Yeah, good. I'm glad you're tracking. So let's do HTTP post, kind of see what this looks like. Surely they have an example. Yeah, I guess that documentation is not bad. I'm trying to just look for like an image to show you, so it's a little bit easier for you to see. This is not bad. Nope, it's terrible too. Okay, have you ever tried to like look at a link? Maybe here, actually. Here's a good link. If I were to go to Google and type in like test, here at the top, you can see that there is a question mark that has appeared now, and it says Q equals test. Now what happens is post requests allow us to submit data to the server, whereas the get request is just telling us to provide. It's just saying like, hey, I'm not sending you anything, so just send me the web page code, and then I'll make the web page look like a web page inside my browser. That's what the get request is doing. The post request is a little bit different. It's saying, hey, I'm actually going to send you data. Like if you log in, like you log into your bank, log into Facebook, etc. Those are HTTP post requests. And you'll typically see those like in logins. So you can see over here, there's actually an HTML form header now captured in the traffic. Now, wouldn't you look at that? User login, user password, user first name, user last name, user email. All captured on the wire. Quentin Brown, thanks for the follow as well. So this looks a little bit different now. And you can see that this packet is actually intertwined with packet 8. And there's a continuation happening over here with some more data streams being exchanged. So let's go and follow that. We're going to follow the TCP stream, first of all. See what we're looking at over here. The beauty of unencrypted communication, yeah. So here you go, right? Like you can see password equals my password. Here is your HTML information captured. And there's a lot of like percentages and weird things going on. And that is the larger topic, but that is encoding. And we're going to get to encoding and encryption later. But encoding just makes this into a format that everyone can understand. So that's something that we're going to look at, I think a little bit later in the side of the cybersecurity content. So for now, just understand that when you put in like my password and test and all that stuff, it's not going to be representative of that inside of the network traffic. So the network traffic actually adds all these like little percentages, signs and such. And this is called HTML encoding. And that's something we're going to look at a little bit later, but this is actually ways to represent characters that might cause errors. So like an exclamation mark could make a server go insane. So instead, it's going to be representative of like %21. A whole other thing we're going to look at later. But just something to kind of bear in mind when you're looking at network traffic right now. Okay. So CI is asking, why does it say TCP not captured? So why do you think it might not say it? What do you think that means? Take a stab at it. Remember what a TCP connection is trying to achieve. It's trying to establish a session. And it does that by setting TCP flags. SYN, SYNAC, and ACK. Take a stab. Knowing that information. Take a best guess. Like, what could that actually mean? Quentin saying, you're welcome. I used to dabble with Wireshark when I was in high school, but had no clue what I was doing. Quentin, Wireshark is a network protocol analyzer. Good stuff, CI. Yeah. So the flags maybe weren't established. Maybe they're out of order, out of sync. We can see like it's highlighted here in yellow. We actually have different flags that were being set in this response right here. So if we did like get account register, this is not typical of like normal TCP flags that you're seeing over here. So something is out of order with the network connection. Now, why it was not captured? Who knows? Like, when we're doing protocol analysis like this, we can make our best guess, but it could be for a number of problems. It could be network congestion. It could be an error in the server. It could be like an HTTP header was not put in properly. The why could be many things. That's deeper forensics and deeper investigation. But the protocol analysis is just letting us know, as you can see here in the info, the TCP previous segment was not captured. So that's an entirely different story. Yep. So, again, not sure why. Who knows? But something in the TCP session got out of order. For whatever reason. Okay. So we've seen some like little HTTP requests happening inside of here. We're going to go to, you can see there's other traffic captured inside this PCAP, and something to be aware of. Finex says you're still unclear as what the error message means. There are probably 10 million error messages out there. I and everyone else will never remember them all. My guess is going to be when it says TCP previous segment not captured, there's probably like a gap or mismatch in the sequence numbers. So something with like the SYN, SYNAC, ACK, or actually show you if it's actually captured here. You see this? And we're going to look at this just shortly here, but there's sequence and acknowledgement number. Something is out of whack here. So let's see. It's 32493519555. Acknowledgement number is 1224. Okay. Those are very different numbers from one another. It says sequence number is 489. This one is 5460. That doesn't make sense to you yet, but that's where the error is. And we're going to see a little bit more about that when we actually look at the three-way handshake. So my initial response was, I and everyone else cannot remember all those error messages. There's really no possible way for anyone to be able to do that. So what I'd recommend to do is maybe type that in. So TCP previous segment not captured. TCP previous segment not captured. Let's take a look at actually the Wireshark website. So yeah, when message Wireshark observes a packet that has a TCP sequence number bigger than we expect it to be in the TCP stream. So that's kind of what I like my gut was saying, right? Sequence of something, expect a sequence of this, but the stream, so yeah, the stream is out of order. And remember what I said, fundamentally, what is TCP trying to do? It's trying to establish a session. If I say A, you say B. If you say B, I say C. If I say C, you say D. Like, it should be a sequence. That's all what TCP is trying to establish. So whether it's this error code or whether it is one of the other 1,000 error codes, something is wrong in that sequence. The session is not being established properly. And that's what I really want to get across. Errors, you need to look them up. You need to determine if they're relative, if they're necessary, and if they're helpful. In this case, this is just letting us know that something got out of order in this request sequence. That's all we know. And we don't know any more than that. Something with those sequence numbers is out of order. Why? Who knows? No idea why that happened in this network capture. Now, if you were on site and you worked inside of an organization and this happened like every 5 minutes, then you would want to investigate. Why every 5 minutes are we having some type of TCP breakdown? Why aren't TCP sessions establishing every 5 minutes? Are we having network congestion? And then you go back, remember that little chart when I said, like, why would there be an error from one endpoint connecting to another stream? You need to go back to that and think, okay, so is the switch operating properly? Is it overloaded? Is the router sending IP addresses properly? Is that overloaded? Is the IP address changing? Maybe something changed along that process. So, something to think about. The error is something, so the process, and we're going to look at more of this side of the help desk. I'm spending a little bit more time on this now because if I look at this, there's probably like, and this is a small capture. If I were to capture something of my own, there's probably like a million things you could ask about that traffic. And if you did that, you would go crazy. You would actually go crazy. And the best part is, you wouldn't even remember it all. You would just be in like this feedback loop of like, what does this mean? Oh, what does this mean? Oh, what does this mean? Oh. And then you're going to be like, well, what was the point of that? So please don't do that. What you do need to do is start to develop that troubleshooting and that sort of like analytical approach of what does this tell me? Is this helpful for me in terms of what I'm trying to achieve? If not, okay, move on. Like yeah, information overload. Like you're gonna go nuts. Quentin is saying, I went to school for computer science for 4 years. I realized it wasn't for you. Yeah, but you love coding? Yeah, I hear you. So I actually really like coding, but I would never want to be a developer. Like an actual professional developer. I like computer science. I like coding. I like game development. And I can do those things well enough, and I still do them on my side, and I want to learn more about them, and I have my own goals with them. But I would never want to be like an actual developer at a company. So it's interesting. You got to find like kind of where you land. Steven saying, I can't imagine being the person looking through Wireshark logs at organization. Okay, so thankfully, Steven, no one at an organization is staring at Wireshark all day. Remember, Wireshark is a protocol analyzer. And consider it to be like a diagnostic tool. You're going to pull it up as needed to perform analysis and inspection and forensics of captured traffic, and then you're done with it. When we get to cybersecurity section, you're going to see we actually start using these tools. They fit under a category called SIMs or SIEMs. And what actually happens is you shove all of those logs to a single dashboard somewhere. And this is where you get something like... oh, man. Okay, ELK Cybersecurity. Dashboard? Can it... Come on, dashboard. Okay, cool. Here you go. So instead of looking at Wireshark all day, you're going to just shove all your logs to a dashboard like this that kind of tells you what's wrong. And, yeah, not all day, but exactly. So, Demorier, but you did have to review captures. Exactly. So remember we talked about sniffing traffic and you record it. I had an issue before where every single day, it was at like 7 p.m. in the evening in the hotel space where I was working, where a bunch of computers would just lose their... They just would not have internet connection. They'd have local area connection, but not outbound. Every single day, it was happening at like 7 p.m. Able to diagnose the issue, there was some type of overload happening between a number of users and requests and server responses only at that time, every single day. It was insane. So, sniff, open up Wireshark, open up protocol analyzers, and look for things like that. That's when you're going to need it. It's a diagnostic analysis and forensics tool. So kind of like Demorier, when they receive traffic from 1,000 points for, yeah, for text. Nice. Karina, so you're asking, Anthony's curious, why would you prefer not to be a developer at a company? I mean, my take on that is just that I find the actual job of software development to be very different than working on software development at home for your own goals and your own interests. Typically, if you're a software developer, your tasks and what you have to code and what you determine are shaped and requested by non-technical audiences that then have to pull in the engineering team to discuss and figure out what's relative and what's actually possible. And yeah, like I was just exactly what Hawk Arbor was saying. It's fun as a hobby, but different when it's a job. Very different experience. Now, some people are fine with that. For me, not so much. I find computer science and software development very interesting and intriguing to do in my own time for my own interests. And if I could just do what I wanted to do in software development and get paid well for it, then that would be great. But that would take a lot of time and whatnot. Like, it, yeah. Dream job would just be like game dev, getting paid just enough, and being content with that. But that's very unrealistic. So it's my dream job. Expectations for management are often, yeah. So something to just kind of keep in mind. Now, that being said, there are some great software development positions out there that are not like that. Like, they're more so like the company founders are software engineers and developers. So their understanding of things and just would make your life easier. That's kind of where you want it to land and stuff. But then some people are like, I don't care. Just like tell me what to write the code and I'll get it done. Again, we've all got our different preferences. Did CoreStack get back to you in the Nmap stuff? No, CI. Well, they did, but it's inconclusive. I don't know what's going on with that. They don't have ClamAV installed, so I need to do some further investigation. I have no idea what happened with that. Anyhow. Steven saying I went to a boot camp to become SD software. Yeah. Realized it wasn't free. Yep. The boot camp wanted us to lie. Oh, that's dirty. Don't ever, yeah, don't lie about your experience. I'm sorry that you have to go through that and we're advised that. Never, ever, ever lie or embellish about your tech experience. It's really, it's just gonna hurt you so bad later on. Just say what you know and what you don't know, and everyone's gonna be happier with it. Karina, if it's okay to ask more, Anthony, why do you prefer cybersecurity and IT? So, okay. I think I might have answered that actually sort of in a different way before, but short answer is I like working with people. I was in hospitality for a number of years. Now, I'm a super introvert, even if you might not think it, and like I go and I have to like shut down after I do a stream for like I need to recharge my batteries. It's easier for me to do because I'm not like talking directly with you. It's like it's a chat. It's kind of easier to work with. But I still like working with people. I like making deep connections, but then I like to be alone. It's just my personality. INFJ, if you follow Myers-Briggs and stuff. So I'm like a walking contradiction. So I like working with people, but then I need to be away from people right after that. So it's kind of weird. But cybersecurity, so IT is directly working with end users with your knowledge of technology. And that's pretty rewarding to be able to set them up for success in their jobs and do their work with your knowledge and passion for IT and tech and hobbyist kind of stuff. So that's really cool. That's why. So your job in IT is to make the end user more productive and be more valuable for a company by enabling them to work with technology. And cybersecurity is a little bit different. It's about protecting them to be able to continue doing their job, but using your understanding and passion of technology. Both are non-revenue generating. Let's keep that in mind. So you're always like constricted by budget, which is kind of fun in a way because you have to be creative like with your solutions. So it's still very, very people oriented. Now I found IT management very fun and rewarding for that reason because it's directly working with other like department heads and finding creative technology solutions with them for their human needs. And then I really liked, and that's why I went to the red team, is because the red team, especially consulting, is very stakeholder and report delivery based. You're working with clients or internal team members and you're walking them through how to solve root cause problems. And I love that. So for me, and that's why I gravitated more to red team, and GRC is similarly. It's very human, people oriented for the most part of your job. So again, that's just a different interest of why. Cybersec is more in the background, right? Not necessarily. That's kind of what I was just talking about there, CI. So if you work as a GRC analyst, you're working with people all day. Like there's meetings like crazy. Some people, it drives them insane. I don't mind that. I actually like conversing and trying to figure out like what the root cause is and map security controls to business requirements. So I actually really enjoy GRC. I find it really important. And the consulting side of things is like that too. It's a lot of report delivery. It's a lot of people oriented as well. Now the blue team can be more like you're not talking to anyone like all day. Like it's kind of like triaging tickets and stuff. So that's why I don't gravitate more that direction. But I find this part of it very interesting. But the day-to-day job for me is not for me. More is saying I have 12 years of security and 6-7 years of retail. You're not funny. 6-7 years of retail would do that, that's for sure. However, you do like solving puzzles, dealing with challenges, investigating how things work, how things happen, and is why I started looking into cybersecurity. Yeah. Yeah. Yeah, thank you. Yeah, yeah. You just got to find where you land. And the cool thing about cybersecurity is you have the whole spectrum. You have work from complete, like super like non-human oriented, like you're just like head buried in the code, all the way to dealing with people 80% of the week. That's the cool thing about cybersecurity. Yeah. That's the cool thing about it. Yeah. Thinking about things there. Stephen Abner, Anthony, do you speak Japanese? Chotto, skoshi. Not much. I actually can read and learn a lot. I can read a lot. I'm just getting to the part where I can hear and I can like watch like an anime or movie or something and understand it. And I'm just starting to study now. Like I need to start working on my output. Same kind of thing. Yeah. Same kind of thing. Same thing with cybersecurity. Yeah, Japanese is fine. Demorian dealing with people, there was a yeah. Yeah, look, I'll tell you this much, alright? The grass is not always greener on the other side, right? You've heard that. I live more now by the belief of the grass is always greener where you water it. That's what I actually believe now. And I believe that all sunshine makes a desert. So, it's about balance. Grass green is likely more manure, yeah. That's a good way to look at it too. I like that. Snow is better. Find what you like. Find what makes you you. Yeah. But cool. We can have a whole talk about philosophical things. Let's get a little bit more on track and then we can talk more about that stuff after. Started the three-way handshake. Let's actually look at this stuff in action. So I think this starts on packet... What does it say over here? Packet 19? Okay, yeah, so packet 19 is correct. Things kick off. Just so we're tracking all the same. Packet 19. Cool. All right. Here we go. Yeah, you're welcome, Karina. Yeah. Oh. Let's fix the posture a little bit. Posture check. Have to... Bad posture sometimes. Sitting down and like... Okay. Three-way handshake. So the three-way handshake, as mentioned before, this is how a TCP session is established. This is it. And this is going to be happening from packets 19 to 21. And you can see it here. And we're going to break it down a little bit more in depth. But you're going to see source IP in packet 19 starts at 10.28.14. So this is the original IP address here. And it is reaching out to 172.253.63.91. Now, how do we know that this is happening as the three-way handshake? There's a series of packets here that happen in order every single time. And you can actually see it here. Sequence 0, acknowledgement 1, sequence 1, acknowledgement 1. Hey, Jay. That's what I was trying to talk about before. And you can see when that starts to happen here, and this is the summarized view. We'll take a look at that deeper in a moment. That is the start. That's how the three-way handshake is established for a TCP session. And then we have a couple other packets that happen of the client hello and server hello. So let's kind of walk through this together and see how this makes sense. Packet 19 a TCP synchronize flag is now being sent from the client to the server. A couple other flags there just for preferences and congestion. But most importantly is the SYN. The SYN flag is initially sent. That means I would like to synchronize with you. There's a dance happening here, okay? The client and server are about to dance, they're about to tango. So the source IP says, hey, I would like to create a TCP session with you so that we have a sequential connection of expected packets to exchange back and forth in order with one another. And in order to do that, we need to establish a sequence and acknowledgement number series so that we can keep everything in order with one another. So, in this case, we can see actually that the sequence number here is interpreted by a Wireshark a little strange, is actually saying that this is the relative sequence number. And that's not really, whoa, let's drop the coffee. That's not actually the sequence number. The sequence number itself, the raw one, is this crazy large value here. 112.860.1888. Okay? Pay attention to, I'm going to actually expand this a little bit. Pay attention to what's happening here between these three. Pay attention to the sequence number and the acknowledgement number and the TCP flags that are being set. So this is the first. This is 1 out of 3 of the three-way handshake. Client to server, SYN flag set, sequence number, acknowledgement numbers have begun. And it's saying sequence is 0, but it's actually this number. It's just Wireshark is telling you relatively that this is 0 because it's easier to refer to 0 instead of that crazy number. Packet 20. The server now responds. The server responds and says SYN ACK, acknowledgement. So synchronize has been acknowledged. Now pay attention what's happened to the sequence number and the acknowledgement number. Okay? The acknowledgement number is actually the sequence number. It's this number right here, 112.860.1888, increased by 1. So the acknowledgement number is now 112.860.1889. And the server responds with a sequence number, randomly generated, of 12770.76107. Now pay attention to this number, again, as I go to the server. The client now responds back with an acknowledgement number that is the server's acknowledgement number incremented by 1. And it responds back with an ACK TCP flag. Now that the server and the client have established a sequence and acknowledgement number of series of incrementing by 1, they will continue to send information back and forth to one another, constantly just incrementing these values by 1. That is how a TCP session is established. The client and server will always know that the next packet coming after should be a constant increment of 1. That's the three-way handshake. This is how, when you log into the bank or somewhere on your web app, your connection always knows what's the next sequence, like what's the next request happening in order, because of these two numbers. And so what Wireshark has done for a visual interpretation to make this easier for you is they've just represented, let's start off with sequence of 0, acknowledge of 1, sequence of 1, acknowledge of 1. That's just an interpretation. That's why it says relative number. It's relative to this TCP session. But the actual numbers underneath it that you can see at the packet level, like on the wire, are actual numbers. And this could be anything. This could be 5, like the sequence number here could be 5. And then on the server back, it would just bump it up to 6. And it would generate a number here of, say, 20. And then what's going to happen here is it's just going to bump up the acknowledgement number to 21. It doesn't matter. It doesn't matter what those numbers are, as long as they're in order. Does that make sense? That's a TCP session being established, which is also known as a three-way handshake. Yeah, for sure. Good stuff, R-double. I'm gonna also put that on a notepad. Yeah, CI, we're gonna get to encryption and stuff after. We're just looking at the three-way handshake right now. So, client to server. That's this packet over here, the first one. And you can see that it sends the sequence number. I'm just going to copy these values out so you can see it as we kind of go. Sequence and acknowledge. It's easier. Okay, so look at the server now coming back. Okay. Okay, so glad you explained the sequence numbers. Okay, I thought so, just checking. Hey guys, sorry I'm late. Hey Doug. Yeah, three handshake support because it's a conversation point to point. Yeah, but what if the recipient is not who they say are? Exactly, yeah. Are you able to verify the Wireshark traffic with some things, one things going over this? Yeah. This is it. This is the three-way handshake happening. Let me just zoom in a little bit here for you. Doesn't like that with the remote stream, so let's go and do zoom. Oh, okay, cool. I can mouse wheel, even better. All right. That's it. That's what's happening. Asheroth, thanks for the follow as well, too. So you can see the client says, hey server, I'd like to make a TCP connection with you to create a session. And it sends a random sequence number with a SYN flag. Oh wait, sorry, 1 second. This is backwards. And then the server to the client takes the acknowledgement number, which is actually just the sequence number incremented by 1, and it sends a new sequence number back to the client. And then the client is going to respond back afterwards, taking that sequence number and incrementing by 1. And it's just going to repeat doing this over and over and over again from now on. They're just going to constantly exchange these numbers, incrementing them by 1. Just be sure, where did the sequence number from SYN A come from? That's randomly generated, Jay. So the server is just going to randomly generate a value like this. And notice now that the client is going to use that for its acknowledgement number of, and it's going to bump it up by 1. And then the next request is going to take this sequence number and bump it up by 1. And then they're just going to keep taking those numbers and swapping places and incrementing them by 1 over and over and over again. And that's why like Wireshark gave this representation here of like 0, 0, 1, 1, 1. So of course the next one would be 2, 1. It has to go up a value. And then these are just TCP flags, which are binary bits of data being set on the connection. So there is a flag TCP header. So like TCP flag header. Let's see if someone's got a good visual of this. Okay, perfect. Here you go. Excellent. This is... Who's got maybe a better visual of this? Yeah, here you go. Perfect. Open image in new tab. Here you go. This is kind of what it would look like at like a conceptual level. The TCP header contains all this information: the source port, destination port, the sequence number, the acknowledgement number. And then it has flags set over here as bits. And then there's a checksum. There's other... Every single one of these packets looks like this. Like it has like data like that. You can see them being represented over here. Here's the checksum, the window scaling factor, the source port, destination port. It's all there. That's so you can see it at the packet level, at like being represented, and then visually imagine like a chunk of data, and that's what we call these headers. It's just a chunk. And it's going to be read 16 bits, 16 bits, and then sequence number is 32 bits, acknowledgement number is 32 bits. That's why those numbers are that size. That's why they're so large. They're 32-bit numbers. And then we see over here that 10 bits are reserved for like header length and reserved bytes or other things beside the flags. That leaves us another 10 bits to be set. Six, 7, 8. Here are your 10 bits of TCP flags that can now be set. See? It's all there. It's all there. So this is why I said you don't need to look at models and flowcharts anymore. Like, you can look at them for reference, but you can get right under the hood now with Wireshark and actually see what this stuff looks like at the binary and like packet level individually. How cool is that? Chris, you fell off your dinosaur. Yeah. Chris, what do you think of this deep dive of a three-way handshake? Yeah, you saw that mug. Yeah, yeah. That's the water. That's the water mug to stay hydrated. And then there's the coffee mug, and then there's the throat coat tea mug, so that I don't get like a sore throat from all the talking. That's a three-way handshake, everyone. Spend your time on this. So CI is saying, so this tool may not be used on the job, but should have some way to analyze network traffic. I mean, Wireshark, you're not going to use like day to day, but you're going to use it kind of like what Demorier said above, like for diagnostics and analysis and inspection and forensics. If you like digital forensics and incident response, you better start getting used to Wireshark. Same like I shared the story to you when we had that weird like 7 p.m. issue going on. We had to pull up Wireshark and inspect the packets. Sorry, you're mapping out your next video was being mentioned, but super grateful. Yeah, it's all good, Chris. I'll see ya. Enjoy. SOC Wonder makes the world a better place. Yeah. Cool. Sounds good. Yeah, Karina. Cool. I think we'll take a little break there, and then we're going to hop into the client hello and server hello. Those are coming up next with the next 2 packets. Yeah, okay, so packet 22, 24. Yeah. Yeah, Doug, I was kind of sharing them. Like, they wait until they see like a proper SIEM, right? Like they haven't seen like full enterprise like investigation and analysis tools. It's gonna be really fun once we get them on that. Yeah. It's really daunting at first. So everyone in the chat, when you first see Wireshark like this, it is very intimidating. But you need to go through it a couple times, like go through the TCP handshake inside of the PCAP and the course material, and just spend time looking at it and making sense out of it, and then make your notes on it, and it will get much, much easier. And then do what we said. Go and record your network traffic at home. Go and record your network traffic at home, and go and try to find a TCP handshake at home. Hint, hint. Some additional challenges are going to be added to the end of networking module that are going to ask you to do things like that. Yeah, I brought up Zeek a little bit earlier too, Doug. I like Zeek. Yeah, we're gonna look at like Zeek later, and maybe like Network Miner. There's some really cool tools, but yeah, agreed with Doug. Start with Wireshark first. It's easier to start with this, and then you start getting more advanced tools. Jay's saying you see a packet called change cipher spec. Yes. So that's actually how attacks happen. Is you can do a downgrade attack from the HTTP side, and even the cipher side. And we're going to talk about that when I come back. I mean, we're not going to talk about that attack, but I'm going to kind of walk you through. It's kind of advanced for now. I'm going to walk you through the client hello and server hello as well. But cool. Let's take a little break, a little breather, stand up, stretch. Kind of do this every hour kind of thing. We'll get back to it. Yeah, Jay, not every website will respect it. They'll just be like, nope, sorry, yeah, it has to be a secure spec. Set that up. Study break. 7-ish minutes. Okay, let's go. Take a break. Stand back up. Stretch. Go do a flip, push-ups, cartwheel, hang from a pull-up bar, go punch, fly kick. Whatever it might be. Just stand up, get moving, and we'll be back. All right. We are back. We're back. Let me break over. Let's keep going. Keep digging into this. So we've covered the TCP handshake, which is effectively the three-way handshake. There's one other session of this, one other part, and that's the TLS handshake. And what this is it's meant to set up encryption. Now, so we're trying to establish an HTTPS. I just damn those one-time push-ups felt so good. Yeah. 1290 push-ups, good stuff. Let's see if we can get everyone to triple their push-up limit by the end of SOC 100. That's a side goal. Or triple your target exercise goal. But yes, so the TLS handshake effectively what it's trying to do is move from an HTTPS connection to an HTTPS. Wait, so move from an HTTP connection to an HTTPS connection. We don't want to stay on HTTP. We want to go and move over to a fully encrypted session. So we do that by, one, establishing the TCP handshake so that we have a session. And now we know to expect communication back from one another. And next we have to go and establish the TLS handshake, which is going to consist of a couple packets. The first one starts at packet 22. And if we look at the protocol, we can see that this is now a new protocol. It's now structured a little bit differently. It's called TLS. TLS version 1.3. And what do we have here? Another header. We have another header added to the packet. And that's what you're going to keep on seeing. Every time we have this type of client-server exchange, it's just a big chunk of different headers on different layers of the OSI model sent back and forth to one another. So now we have a new header. We have a TLS header, a transport layer security header. And we can see here the content type is, well, the handshake. And what is the protocol? It is the client hello protocol. So what happens here is a list of supported cipher suites, which are called like encryption algorithms, we're going to learn about that later, is sent from the client. And the client also is going to generate a random number. It's called a client random, right? Or is that... Yeah, client random. So we'll see this number also being generated along with the supported types of cipher suites. So it's saying we have 16 cipher suites that we support. TLS, AES 128, Galois something. Oh man, haven't remembered what that is in a long time. GCM. Those of you studying the Sec Plus probably remember these things like more broken down. AES 128-bit encryption, AES 256-bit encryption, etc. These are all the cipher suites that are available. So when we say cipher suite, we're saying essentially a bunch of mathematical formulas, which are algorithms, that we can process our packets with, and it'll be fully encrypted. And we'll get back to the encryption later, like I said. Just a note for all intents and purposes that we are saying, hey, I'm the client, I'd like to encrypt this connection, and here are the algorithms that I can support. What do you support? That's effectively what's happening here. And we can see this by the client hello. The client hello is the start of this handshake. Okay. Now, we have another exchange. Saying if you all want to be in one of the live study rooms, anyone wants to cover or just play around a Wireshark or notes, yeah, cool. Now we can see the response back on packet 24. And this is the server hello. And what's happening here is the server is going to choose from a list that the client supports. It's going to grab one that seems to be the most suitable, that they both support back and forth with one another and whatever is necessary. It's also going to send back a randomly generated server random key for the generation. This is that key exchange happening in place. It's also going to provide the server's public key used, that we talked a little bit about, how we had that private public key generation and a session key being generated over here. Again, we'll come back to that, but just know that this is a server hello happening in place right now, along with another random ID generated by the server. Now, the server has agreed on Cipher Suite TLS AES 128 GCM SHA 256. It says, okay, that's cool. I can work with that. Over here, you can find the actual key being exchanged. That is effectively kind of what happens. So the client is now going to encrypt some type of secret. So it could be like a number 5. Okay, let's go with 5. The client is going to encrypt the number 5 with the server's public key. And it's going to send it over to the server. The server can understand that because it can use its private key. Now, what happens is they've established some level of trust. Now, the client and server are actually going to do some deeper functions. They're actually going to take the client random and the server random. They're going to combine them together with the algorithm. They're going to encrypt it with one another and establish a fully encrypted session afterwards by taking in various data points that they both generated, both on the same TCP sequence. So we should have a sequence of sequence and acknowledgement numbers, both incrementing by 1. We should also have client and server random generated numbers. And we're going to take all that information, and then we're going to use a new encrypted key that we can both decrypt together, and then use that encrypted key for all communication from then on. And that key is actually called a symmetric encryption key, which is different than the public and private key. Symmetric keys can encrypt and decrypt with the same key. So this is what's happening here. We're establishing we're establishing a symmetric key that we can share with one another that no one else can read, and then we can now encrypt communication back and forth with one another on that matter. Now, all of this is going to be happening. Everything that I just mentioned sort of now happens over the next little bit. As you can see, like encrypted application data, we can't read this anymore. All of this starts that encryption sequence. We're gonna dive into that more in the encryption module, like I said. So what you need to understand right at this point in time is when we start seeing an encrypted connection, there will be a client hello and a server hello that follow the original TCP handshake. And that is the TLS handshake that's happening. And the TLS handshake is the client saying, I can use these algorithms. What do you want to use? Server says, let's choose this one. And here is my certificate. Here's my ID. And here's my public key. Now go ahead and generate a special key and decrypt it. Sorry, and then encrypt it with my public key. Client encrypts it with the public key, sends it back to the server. Server decrypts it and says, okay, so they're using my key. Now let's do this process with a shared key now from now on. That's really it. And the trust happens by taking in that client random and the server random together. Question says, isn't it scary that Wireshark and probably a man in the middle can read the shared key? They can't. That's the thing. They can't read the shared key. The shared key has... So one part of it has been encrypted by the public key. And then only the server can decrypt that with its private key. And then the server is going to package up some more information, and they're going to do that exchange again. And it's the thing is, it's made up with the client random and the server random. So Jason, so that is the Wireshark before it has been encrypted with the client's public key. Yeah, so that's what I was trying to say. So once we get past the client server hello, these TCP packets are just general exchange happening back and forth. There's nothing encrypted. But now take a look at the application data. It's now encrypted. We've now moved to encrypted communications from here on out. Encrypted application data, encrypted application data. This is the client and server both exchanging using the algorithm back and forth with one another. And they're using keys that only they know. So, kind of recap a little bit more at a high level. Actually, so I can have something to reference while I talk. I'll keep probably change. You're okay, I guess. Well, the public private key is only established to be able to share a session symmetric key, because that's way more efficient. It's fast. It's super fast. Public private key encryption is actually very slow. I'm just trying to see if someone has a decent model. We're going to get into this a little bit more, don't get me wrong, but what's happening is, let's see, pre-master secret key exchange. Maybe someone's got a better model on that. Otherwise, I'm going to have to... Actually, here. This is perfect. Okay. Yeah, it's all good, Jay. Okay. Here is what's happening. This might be a little bit easier to understand for this encryption. And then, again, we're going to dive even more later. The client is actually generating a one-time session key over here. Okay, the client is generating this pre-master secret, if you want to call it that. Okay, it's a secret value, and the client is going to encrypt it with the server's public key at that point in time. Now, the server is going to take it and decrypt that secret value. And remember, the server can only decrypt it because it gave its public key for the encryption. So that means the server's private key can decrypt it. Now, what happens is they take this secret, they take it with the client random, server random. So there's effectively three things. So that they're creating a unique recipe with values that only they know. No one else knows what these values are right now. No one. You can't read it. No one else could read the session key because the client encrypted it with the server's public key. So you can't get a man in the middle happening here at this time. Does that kind of explain a little bit more, Jay? Wireshark is able to read it because it has the public key inside the traffic, but it's not decrypting it. No. That's why you can see later here, after the server responded back, you see the server random, cipher suite, and you see key share. Here's the key exchange. The server sent its public key. And then the next change in the TLS connection from then on, the client is effectively, the client server, they're now going to just use keys back and forth to exchange encrypted data. Yeah. So yeah, so this is symmetric because two different keys. No. So take a look back at that image. Public and private key is just for verification. That's it. And through that process, they're going to generate a symmetric key that only they can read back and forth with one another. And the symmetric key is faster. You don't need to worry about public-private key at that point. You can just encrypt it fully like we've seen inside of the packet. You can see now, it's like we have encrypted exchange happening here. Encrypted application data. Encrypted application data. I can't read this anymore. Yeah. Symmetric uses one key. It's the same key. And asymmetric uses two keys. With symmetric, the same key can encrypt and decrypt. Yeah, just as Jay's saying. Now, like I said, we're going to come back to that a little bit more in cryptography because this actually gets a little bit more in depth. So don't get too overhead right now. For now, just understand that there's a client hello and a server hello that perform a key exchange with one another. That key exchange is to get a shared symmetric key back and forth with one another that only they can read using public and private keys to encrypt data with trusted data inside the connection, like the client random, server random. And there's that the client is generating a secret that only the client knows and is never ever encrypted. It's never in clear text. You can never see it on the wire. It's encrypted. The client is encrypting the shared secret with the server's public key. So you can't get in the middle of this at this point. And that's why you start to see this exchange happening here of encrypted data from then on. So let's take a look at packet 19. And this is one big sequence, right? So we're going to go here and let's actually look at this together, follow a TCP stream. This is what it looks like now. That's what happens over the wire. Yeah. Yeah, this is ciphertext now. You can't read it anymore. They're just encrypting communication back and forth with one another. Now, that's a far cry from packet 7, right? Follow? TCP stream? You can read all this. I can see the password, I can see the email, everything. Yeah. Oh, Jay, the only difference is the conversation. So, from the server to the client is this, and from the client to the server is all this, just like junk, all this plain text, non-encrypted stuff. So blue and red is just color notation for server and client. So. So here, I'll also do this just on this side. So this kind of makes a little bit more sense, like we did with the handshake. And again, we're gonna come back to it. Yeah, Wireshark is awesome. Okay, so TLS handshake. Okay, client to server. Let's kind of walk through this together, right? Client, hello. I have cipher suites. Which one you want to use? 2. Server to client. Server, hello. Let's use cipher suite A, which is 128-bit. Here's my public key. Oh, sorry, I also forgot client random equals 1, 2, 3, whatever. Okay, so a couple things happen there. Here's my public key. Let's kind of do this actually. Do that. See in the chat whether Jay's excited. Yeah. Let's use Cyber Suite A, which is 128-bit. Use my public key. Server random equals 456. Okay. Client now. Okay, so this is not happening online. Client offline generates secret secret key, secret session, whatever. Let's call this master. Pre-master secret. Scripts. Okay, so that's kind of, yeah, so that's kind of what's happened so far. Okay, so client sends, let's call this step 4. Client sends info yeah, so I'm just trying to keep this like super high level for now. Just kind of like, let's just like walk through it, generally understand that there's a key exchange of stuff that happens at this point in time. Send encrypted session key. Or sorry, encrypted pre-master secret key. Okay. Server offline. So now server has obtained client's secret key. Server can decrypt it with server's private key. Now, the server has effectively 3 values now, okay? Server has secret, client random, server random. Has these 3 pieces of information, okay? Now, what it's going to do put these into a, I think it's called the KDF. Yeah, KDF, key derivation function. And what's happening here is both the server and the client have the same information now. Okay. Client. Client has secret, client random, server random. Put these into KDF. KDF, for all intents and purposes, is the cipher suite. Okay, let's just call it that for now. So you can see at this point in time, server and client have the same information that they can generate a symmetric key with. This is the session key. The only way this can break is if someone gets the server's private key. That's why you hear so much about like, oh my god, like they got the private key. Because only the private key can decrypt the initial secret. Yeah, Jay. I'm trying to keep it high level for now, but yeah, call this the function, the pseudo-random function that is effectively, they're both doing the same thing now. So 7, client now have a symmetric key. Yeah. Yeah, this is, like I said, this starts to get a little too complicated. That's why I want to keep it just simple for now. Yeah. Does that make sense? Or sense enough? Yeah. Okay, cool. For now, just remember that Remember when I said early on that encryption is math? Let's go super simple. 1 plus 1 is always going to equal 2 in this case, right? 1 plus 1 is 2. Let's just agree on that. This is effectively like saying secret plus client random plus server random equals 2. Okay? So from now on, as long as we're both using the encryption of 2, right? As long as we're both doing this with our data, and only we have the same secret key, no one else does, because it was encrypted before, then all communication now is going to be encrypted from now on. We're going to get much more into like the deeper weeds of like the terms and definitions and all that stuff later, but at a high level, that is effectively what has happened. Walk through it one more time. Client goes to the server, says, hey, I have cipher suites. Which one do you want to use? Also, here's a random value. Everyone can read this still. That's fine. Okay. Server says, hey, I got your message. Let's use cipher suite A that you said we can use. Let's just go with 128-bit. Also, here's my public key. Whatever you use this key with, only I can then read. Okay, that's kind of what's happened there. Also, server random, here's another value for you. It's just 456. Cool. So the client says, all right, cool. I'm going to generate a secret, like a secret value. And then I'm going to encrypt that secret value. And I'm going to use your key. And only you can read it after that. So the client is going to send that over. The server now has obtained this secret that the client gave with their public key, and the server can read it because they have the other key that can open up that lock, which is called the private key. So now the server has the secret from the client, has the client random and the server random, and it puts this into a blender called the KDF, key derivation function. And it puts out a value, like another secret key. This is your symmetric key right here of 2. Let's just call it that. It's just 2. The client also has the same data. It has the secret that it encrypted, that it hasn't sent out in clear text. It also has a client random and the server random. It also puts it in the blender. And because it's math, it comes out with the same value. So now they both have this same mathematical formula that they can both put data into and blend, and that they can both decrypt. Does that make more sense as another little walkthrough? At a high level, okay, cool. Good. That is how encryption happens. Yes, it's, you know, a little walkthrough at the end always helps. Yeah. Yeah, after that kind of rant, I have to drink some water. Cool. That's encryption, everyone. That's the three-way handshake. That's the TLS handshake. That is how the whole world goes around. So how does this break? If someone gets the private key, all of this fails. This is why you hear private key management is such a big deal. The private key the server has to decrypt its public key. The private key doesn't decrypt the public key. The private key can unlock anything that the public key locks up. Think about it like that. That's a better way to think about it. Is the private key always stored locally? Yes. On the server, in this case, yes. Now, in more bigger businesses, excuse me, excuse me, in the bigger businesses, you are going to have key management and key rotations and these other big things that keep the keys very safe between many layers and basically multiple versions of this public key exchange. Ultimately, so that the last one doesn't fail. And it gets harder and harder and harder to get to that last key. So ideally, no, you don't want to store your private key on the server like that in the future in a much more secure environment. And that's what enterprise environments do. But for this situation, like if you did this at home and you just connected between two browsers, they would just do it with inside the browser, and that would be the end of it. And that's kind of what's happening here. So if I were to go to, let's go to, I guess, google.com, and let's go to google.com. Okay. If I go up here now inside this browser, and I go to connection is secure, certificate is valid. You see this? Here's the public key of google.com. Here is a certificate, another key, that if I were to go, and we're going to look at this later, this is another authority saying that you can trust Google. So I'm trusting this authority, and it's just multiple layers of trust. But if I were to take this public key off of google.com, and if I were to encrypt anything with it, then only google.com could read it. Xenofail says, so gain access and steal the private key, then encrypt message? Yes. That's what people want. They want that private key, because if you can get it, damn. You just won. Good game. Yeah. GG's. Okay. Stretch. There we go. Cool. That's how the world goes round. And the cool thing is you can see all that in Wireshark. Yeah. Sweet. Okay, so next thing we're going to take a look at, so we got an hour-ish here to go. So next thing we want to take a look at is HTTP requests and headers. We talked a little bit about it, but what I actually wanted to do... Oh, wow, this still has our old website. I need to update that. I apologize. I don't even think... Is that still online? No, it's not. We took that server offline. So I apologize. I need to update that and make a note in the lab. We recently took that server offline. Okay, so what I want to do is I want to go and open up a new tab, and I want to go to... What do we say inside the lab here? Google.com, example.com. Okay. Let's go to google.com. We'll take a little break after this, because this one's sort of short. Yeah. All right, so if I go to google.com and I right-click anywhere here in the web page, and I go to inspect, okay, got a whole bunch of stuff happening, and we're on the lab now, HTTP requests and headers. And if I go to the network tab, every browser has these inspector tools inside of it. Let's go to the network tab. And what I want to do, I'm going to clear the log. There's like a little button up here. And so if you're using Firefox or whatever browser, they're all the same. They all have some type of web developer tools like this, typically called like the inspector. So sorry, it's called inspect. Inspector is the thing over here in the element. But if we go here, and these are called dev tools actually. If I go and if I refresh this page right now, the browser actually also shows you all of the HTTP types of requests and network requests going on as well. Not as much as Wireshark will show you, but it shows you a ton. So here is the HTTP GET request for going to google.com. And these are all of the response headers. And these are the request headers that we saw inside of Wireshark. Here's the GET, here's the path, scheme. This is what we accept. Here are session tracking cookies that are used at the application layer. A whole bunch of stuff. This is how HTTP requests work. And the reason why we kind of stop here is just to show you what's actually happening at like this application layer level and get a little bit outside of Wireshark. Now let's move over to like example.com because that's a little bit quieter. Google's really noisy. And I'm going to refresh this page now. And notice over here, we have example.com and detector.js, right? Not a lot going on at the network level. So you can see how much Google's actually tracking. That's why people freak out. Google, right click, inspect, network tab, and do a proper refresh. Look at all of this like stuff happening in the back end. And we take a look at this HTTP request. Take a look at all these like these headers. There's so much happening here. All of these cookies are trackers. Like line by line, these are trackers. All of them. Tracking everything. Now look at the difference between something like example.com. One request. Jay's getting late. Yeah, cool. Have a good rest of the night. Thanks for coming by. Thanks for being here today. Look at the difference between something like example.com. Very, very different. And take a look at this header. We can see it here as well. User agent, we've seen that before. Windows NT, Windows 64-bit, and we support various types of browsers. What else do we have here? You can see the request codes, 304, not modified. And there's a whole bunch of this stuff. HTTP response status codes, let's take a look. These are categories like informational, success, redirection, client error, server errors. These are going to be very important for you to learn and know in cybersecurity. IT, not as much, because you're not really dealing with too much, but cybersecurity, yes, you're going to be looking at these headers a lot. Because this is how you're going to track attackers. So I also wanted to, hey Ruben, thanks for the follow. So something that I wanted to highlight here. So we've been living inside of Wireshark at the packet level, performing all this inspection that we can look at these different PCAPs. But there's a lot you could do at the browser level as well too for inspecting types of different responses happening. Now, what I'm trying to highlight with all of this, and the reason why we stop here to talk about HTTP, is because this is effectively a stateless protocol. Oops. Everything here that's happening inside of this request is just a snapshot in time. So when we start doing network traffic analysis and malware traffic analysis, it is going to be very important for you to start understanding codes, like response codes. What is the response of things happening? And there's reasons for this. If I get something like a 200 OK, that means we're good. We're in the clear, right? Like it's a success. It doesn't mean that it's secure, but it means it's a success. But if I get something maybe like a 301, if I went to google.com and I got a 301 saying it sent me somewhere else to like supergoogle.com, something's wrong. That would be like an example. And I would know that by looking at the HTTP code of 301, redirecting me, sending me somewhere else. So we stop over here for a moment just to kind of talk about how it's one thing to just generally understand, like, it's good to understand how this is all happening. And now we need to start upping our game and start working with just like pure protocol inspection, which is what we're going to do now. We're going to jump into looking at HTTP based traffic for that, like weird events going on, and tracking it down in the next two labs. So for those of you that don't have Wireshark installed for now, which you should afterwards, you can go to any website right now and start doing inspection of what's happening at the network level of these websites. So you go inside here, you can go clear your cache and whatnot. You can override the headers if you want, kind of change them around. There's a lot of stuff you could do. I think it's a little bit easier inside of Firefox. But go and start learning and paying attention to what requests look like. So if I went to example.com and I see something like a 304, well, what does that mean? So 304 says this is used for caching purposes. It tells the client the response has not been modified, so the client can continue to use the same cached version of the response. So what does that tell you? It tells you that I've been here before, and I didn't have to make a whole new request. So yes, CI, you can go to any web page and right click, and depending on your browser, you're going to have something that says like inspect. And you go inside here, and then you can go deeper, and these are called like developer tools. And then go to the network tab, which is pretty common in them, and you can see afterwards by refreshing the page what is actually happening here at the high level layers like HTTP and such. Yeah, F12 works as well. Yeah, nice. Works at the VM too. So I want you to start getting familiar with the layout of what this generally looks like. Response headers, request headers, just to understand what they look like for now. Cool? All right, let's take a little break there too. We'll come back and do the last little bit. And as always, we'll run a quick ad here in the break so we're not missing anything, but we'll be back. All right. All right, all right, all right. All right, we're back. All this stuff. Cool. Okay, so now let's move on to the next lab. Yeah, we're gonna do a little bit of protocol following now. Right, for this one. Just a little bit more experience and exposure, and what we want to do is track down some DNS requests to a stream and identify what the protocol is actually being used for in the traffic, because it's on a non-standard port. And then we've got some TCP handshake analysis to perform. So now we're going to actually start applying some filters instead of just kind of at a high level looking at a packet. So this is going to be our introduction to that. So let's go ahead and open up this next PCAP. This is actually going to be in the ops PCAP. That's right. This is inside of an S3 bucket. So let's go ahead and open up a browser instead. Do I play games in VR? Yeah. I grabbed the Quest 3 before. I enjoy it. It's fun. I really want to see VR take off, personally. So let's go ahead and take this file and download that. So this is in addition to the files inside of your lab folder. Let's go and open up our downloads. Actually grab that. Put that inside here. Yeah, the Batman one does look pretty good. Yeah, I'm gonna check out some more. It was an ad, yeah. Yeah, some random ads will pop up. You must have looked at it before then. See, those are your ads. They're trying to get you. They want you to play Batman. Cool, so let's go and open up the Ops PCAP. Alright, so this is a lot more. It's a much bigger PCAP. What do we got here? We have all the way from packet 1 to 33,000. 30, almost 34,000 packets. It's a little bit. You can't just go and scroll through it this time. If you try, right? There's like, you see some like bad requests happening. Something out of the TCP sequence order got screwed up. Got a bunch of different color-coded things. So, this lab is following protocols. Karina, your ads don't seem targeted. I don't know. Maybe you are blocking your ads? You have an ad blocker or something? Or maybe you just saw something that Twitch wants you to see. But ads are typically targeted to you or like your home network. Typically. Cool, so now lab following protocols. Let's hop in this. So what we want to do This lab is really, like I said, it's meant to get used to using filters, because we haven't done that really yet. We've just been looking at very trimmed out PCAPs. Yes, yeah, you don't see it in the ops folder. You have to download it off the first step over here, the ops PCAP. Go ahead and download that and bring that inside your folder. Or just open it up. Download it and open it up. That's step 1. So this lab, we want you to do a little bit of analysis on DNS, TCP, and HTTP. We want you to start applying filters to get used to working with that. So let's track down. We want to start off with DNS. And we actually want to track down a certain A record here to put us in the right direction. So we're going to go and type in DNS. And the first one that comes up on packet 15 is we have a standard query for an A record of horizons.jpl.nasa.gov. So if we wanted now, instead of looking at all the DNS traffic, let's do something different. We can do DNS dot, and as soon as we do a DNS dot on the filter bar, I'm actually going to zoom in a little bit more now. Didn't help at all, did it? Sorry, the filter bar doesn't change. Okay, so if I do DNS dot, you can now see all of the available additional methods we can search with DNS for. And remember, if you're never sure, you can go to Wireshark filters list, and the display filter reference right from Wireshark itself is going to give you everything you need. So you can click on D, and we're going to find DNS. I can just do like a Control F. So here we go, DNS domain name system. Let's click on that. And here's all of those filters for you from a website point of view with a slight description of what it is. So what we're looking for is DNS query. So I'll do query. Yes. QRY. DNS query.aim. So I'll preface this with the Wireshark filters. Some will be like English language. Some are going to be really shortened almost for no reason. Like response, I can understand. QRY, I feel like that could have been another character or two to get to query. Personal rent. Anyways, so you're going to look them up as you go. DNS Q. That's a little bit easier to kind of see what they are. And what we're looking for is DNS query name. And the convention for filters in Wireshark are a little different than what you'd expect. You'd have to put like an equal equal. And what I want is horizons .jpl .jpl.nasa.gov. Cool. So notice how it turned green, right? It goes from red to green. When I'm still typing this, this is an invalid filter. It's not going to find anything. When I make this proper, it will give a green visual cue. If I put one equal sign, you can see it's not going to work. And this is just a convention of how to work with it. So do that. DNS.query.name equals horizons.jpl.nasa.gov. And now I've actually been able to obtain all of the DNS queries as it would pertain to horizons.jpl.nasa.gov for the DNS protocol. That's much better than trying to find a random DNS query of horizons.jpl.nasa.gov and all of the DNS records. So kind of show you the difference again. If I do a DNS search, well, I get everything. There's level effect inside here, you name it. Ton of traffic. But if I want just one record or one domain, I can search just for this. Much easier. So let's take a look. And DNS query responses in packet 21. Okay, so here is the response. A record. Answer. IP address. We have our IP address here. Sweet. That's what we wanted. we're going to copy this value. Now let's go and filter all of the traffic that went to this IP address inside of this capture. So I could go use the IP protocol dot, if I type in D, if you can see, if I'm looking for destination, IP.dst, so destination, equals, copy paste that in, 137.78.251.144. So now I'm able to filter out for all destination IP address related information to the Horizons JPL NASA Gov domain. Cool. So you see how I'm getting deeper and deeper and more like precise with my searches. Now I have this ability over here for me. So what I would like to see is, are there any TCP handshakes happening here inside of the traffic? Now, I think we could maybe... we could go and do some searching for that. I think that, what does the lab say? It's packet. Sorry, off too much. Yeah, packet 24. Right in the beginning. Packet 24 starts this SYN. Okay, so let's go ahead and follow that. Follow TCP stream. And take a look at this. This is interesting. So warning, property of the United States government. Interesting. This computer is funded by the United States government and operated by the California Institute of Technology, is supportive of ongoing U.S. government programs and activities. If you are not authorized to access the system, disconnect now. Uh-oh. Users of the system have no expectation of privacy. By continuing, you consent to your keystrokes and data being monitored. Interesting. So what's going on with this PCAP? We've got Horizons Online Ephemeris system. Type system news. Now, if you did a little bit of Googling and kind of like searching around over here, you would actually see that this is the Telnet protocol in action. But the odd thing going on is this is on port 6775. So remember when I said before that it doesn't matter so much, like there are standard ports that we can use, but you might find that protocols will be in use in different ports. And that's fine. As long as your configuration permits it and it's supported for it, then you might have Telnet on a different protocol, or sorry, on a different port. Now, again, we know that because like we kind of poked around in some analysis on what this output looked like. That would probably bring us to Telnet itself. At this point, it's just a TCP connection happening, exchanging data back and forth to one another. So if I were to copy this, go to Google. See if this guy actually going to bring anything up. Nope. Cool. Just kind of curious. So a Telnet connection, you can read everything in the clear. Very interesting. So now that we know that this is a Telnet connection, was there a TCP handshake that happened? So we could do that. Let's just filter first to see if there's any actual TCP port equals 23. So what it looks like over here is that some type of three-way handshake actually occurred much later on inside of the connection. So there was I'll go back. So we'll go to IP destination 137.78.251.144. Hit enter. Let's go right to the beginning. So it looks like there was a lot of traffic that went there for whatever reason. And if we follow the TCP stream at this point, all of these packets are actually only indicating, at this point in time, this message. So, like, look, this might look small, but I just want to kind of point something out to you. If I click, like, on each area here, this is actually going to take me further down the packet list. This stream is representative of multiple packets. So don't just think like this is just like one packet happening. So Karina's asking, sorry, could you review how you got to the JPL stream? Yeah. So first I did a DNS query .name for horizons.jpl.nasa.gov. And then I hit enter. Whoops, I'm still in the chat, okay. And hit enter. And I found a DNS query for the A record of horizons.jpl.nasa.gov. And the response is in packet 21 with the address of 137.78.251.144. So I'm going to copy this value. And then I'm going to run an IP.destination equals that IP. I'm just trying to track down like what's happening with this connection in this stream, just following the protocol. And I can see in the beginning that there is some destination IP address traffic starting at packet 24 that seems to go down to packet 90. So I right-clicked this and I went to follow TCP stream just to see what's happening. So this is a very long TCP stream of information that I can now observe some input. But what I'm trying to figure out now is, well, was there a connection made? Because this to me is Telnet traffic. And I know that, and I'm just kind of speeding it up. If you went and did a bunch of Googling and you didn't know, you probably would come across activity that looks like this with like a login form. So we're just kind of helping you along saying like this is a TCP Telnet initiation happening. However, it's happening on port 67735, which is kind of throwing you off a little bit. So what I want to find out was there a TCP connection that happened with this IP address now? And it seems to be that there is something that happens over here. There is some type of encrypted connection that's happening with that IP. Now, there's HTTPS activity, but that's browser related. Was there a connection made on this TCP stream here after this? So in order to do this, we could do something like TCP.port equals 23. And interestingly enough, there is actually a Telnet session that's been established. Now it's going to a different IP address. So let's go and follow this, see what happened. Follow TCP stream. Cool. Okay. So it looks like some kind of connection was made on Telnet much later on. And it looks like the traffic got redirected to, I believe, another IP address actually. Yeah. So now we see a Telnet connection happening in place, weather, data, command one of the following. So some type of communication, username, none, password, none, not correct. So someone in this traffic is trying to log into this connection. That's interesting. So that's kind of where that ends, though. Let's take a look see. We know that there's some handshakes happening inside of this traffic, right? So let's see if I were to think about this, like I want to go and find the beginning of three-way handshakes inside of this PCAP for further additional TCP sessions, but maybe on another common protocol like HTTP. Well, for that I can maybe go and do TCP dot flags dot SYN. So the SYN flag, member, equals 1. And now I can actually use some more operators, kind of like we've seen in the command line. And I can say, well, I want one condition of all TCP flags being set to 1. That's 1. But I'm still going to get a ton of noise that way. A lot of weird packets. So, and I'm going to say so ampersand. TCP.port is equal to 80. So you can actually chain filters together. So what do we see here? We see a connection made we have a couple of them happening over here, actually. So source 192 going to 7.6. And this looks like one giant session. Here's another small one. It's sort of connected, actually. So let's see. Let's do some following. Follow. TCP stream. Nothing in that case that we're actually able to read. There's no data that's being sent. Okay. Go back to our filter. Let's take a look at this next one. Follow this stream. Follow TCP stream. Interesting. Okay. So the rest of this traffic now. So there was a request made in this PCAP taking us to host leveleffect.com, a GET request, user agent Windows 10, 64-bit. Accepting general language that we would expect. We want to keep the connection alive. And the server responds back that with a 301 has been moved permanently. It's actually been moved to HTTPS. So pay attention to what happened there. A GET request with just HTTP, so non-secure, was made to leveleffect.com. And the server responded and said, whoa, actually, you need to go to https.leveleffect.com. So that's a little bit different there. So let's say we wanted to get a little bit more specific on this filter. We could do something like TCP flags.syn equals to 1. So that's one thing we want. And we want TCP.port is equal to 80. And IP.address is equal to, what is that? 76.223.227.102. Yeah. So let's see just flags related to this. Did I type that in correctly? Not have. I think I had an extra 2. Yeah. Yep. Yep. Had too many 2s. Okay, so now I can actually get a much more specific view of just the three-way handshake happening between this location, but also capturing the redirect. So if I wanted to do a search now, because the other trail kind of went cold of whatever I was searching, and mind over bytes, thanks for the follow as well. So that trail went cold, but if I then... So I'm just kind of like just following and seeing what happened, and looking for TCP handshakes and such, which I found, but I also found another TCP handshake connecting out to leveleffect.com. But it failed. It failed because it got an HTTP redirect to 301, forcing it to go and create an HTTPS connection, which we should then theoretically see a client hello and server hello, right? We should. So this is happening at like packet 660. So let's go and close that up, and let's do actually now traffic inspection for TCP.port equal to 443. And wouldn't you know it, where are we? Yeah, we're over here. So a little bit after packet 663, we are now seeing a client hello. Take a look. Gonna kind of scroll back down. Whoops. Cool. Okay. So what I did here was I added a little bit more to the filter. And I wanted to know, like, I want to actually see this redirect happen. So we had the GET request, right? Happen to leveleffect.com. We got a 301 redirect that told us where to go. And then immediately after, we see the connection happening of where to go. Here's the client hello. And there's the server hello initiating the key exchange that we saw previously. Now, what this is also telling us is that we actually won't be able to inspect whatever traffic happens over here at this point in time, right? So if I were to say, because this looks like it's going to somewhere else, 76223.27.102. This now is changing. Client hello, server hello, server key exchange, hello done, client key exchange, encrypted handshake message, and now application data, application data, application data. So the trail went cold over there at that point in time. Then there's some other random traffic over there. But yeah, small little lab just to kind of get used to working with different filters and kind of chasing down and following protocols and what happened. So to kind of recap, right? We started off just we wanted to find out what was going on with this DNS record over here. And I think that's the end of the lab, right? Just double checking. Yeah, okay, cool. So we start off the lab over here just to identify some information related to a suspect or maybe just like a unique DNS record. So we saw a domain of horizons.jpl.nasa.gov, and we tracked it down by performing a DNS query.name filter search just for that filter, sorry, just for that domain. And that yielded us to an unestablished TCP connection, but it looked like Telnet. So then we did a search for Telnet on TCP port 23. And we saw later on that there actually was an established connection that happened between those connections. It just went over to a different port. So the TCP connection started on port 6775, but it carried over to port 23 with a proper Telnet connection. And then we observed the traffic between the two where there was some requests happening and taking place. And that seemed to be the end of that. But during that exchange, we also observed another TCP handshake happening. There seemed to be one other one right after that. And that actually went to leveleffect.com. But in the initiation of the TCP handshake, with the SYN flags being set, we saw that we got a redirect, an HTTP 301 code that told us, wait a minute, we're not going to accept HTTP. This needs to be an HTTPS connection. So we chased that connection down a little bit further, and we were able to obtain the client hello and server hello at that point. That's really that lab. Just a little fun exercise to go and get a little bit used to filters and tracking stuff down. That's really it. So Wireshark is not so much just about starting from here and kind of scrolling through. You can perform more surgical and like precision-based analysis, hunting down different traffics and protocols. Yeah, you're welcome, Karina. That's really it. Just a little bit of exposure experience to help you get used to working with filters and different operators. I think we'll have time to do a little bit more of another one and then carry it over next lab. So the reason that we moved from 6775 to 23 was because the TCP connection didn't go any further on that port. It stopped. But when we followed the TCP stream, it looked like Telnet traffic. Like that's what Telnet traffic actually looks like. So if I were to go and do something like this, Telnet, you can kind of see that same repetition, because Telnet actually kind of echoes things back and forth. So what we're trying to do in the lab is just kind of nudge you along so you don't get stuck with that, but just demonstrate to you that we actually observe Telnet traffic. And then if we went to Telnet, standard port, it's actually 23. So we said, wait a minute, that's kind of strange to have Telnet traffic on port 6775. Did anything happen after with Telnet? So then that gave us the reason to search for TCP port 23, which, surely enough, provided an actual TCP handshake and a connection with some data exchange between the two. That's why we chased it. And yeah, Doug's going to go over some more. It's a lot of repetition when it comes to protocol analysis. Don't get too hung up on the filters as much as you're just trying to identify objectives. So let's get some more reps under the belt, and we're going to go and work with... We're going to move on to the next lab and just at least get it started. I don't think we're going to be able to complete it, but we're going to move over now to network traffic analysis, endpoint metadata. And so now we're actually going to put it all together. We're going to put this all together now. And this lab is about finding information. Zeno saying, are you trying to redirect JPL users to LevelFact? No. No. We were just doing some packet inspection and just following some protocols. They were completely unrelated. It's just we happened to also see another TCP handshake happening in the traffic to leveleffect.com. And then we just chased that too. We're like, okay, cool. Like, what happened? And it looks like there wasn't a full TCP handshake. Instead, it was a 301 redirect to establish an HTTP session. So it was just another investigation to find out like, oh, well, like what happened with that handshake? Because there was another one right after. So whoever this user was, they were doing some interesting stuff on Telnet for whatever reason, and they decided to visit the Level Effect webpage as well along the way. That's all. And the exercise of that lab was just getting more familiar with filters and chasing protocols a little bit. So, cool. Let's do a little bit more before we wrap up for the day. And so when you see source destination IPs communicate for ports, yeah, you want to chase it down. Exactly it. We're going to learn more about, like, by the end, actually the next lab is going to get us into malware traffic analysis. You will learn about like attacker patterns and behaviors and how to match that up to what you're seeing. First things first, you just got to get a little bit used to things. So let's get some more reps under the belt with Wireshark, and we're going to perform endpoint metadata analysis. And we actually want to answer some questions as an exercise. Imagine doing some cardio. That's what we're doing right now. Some Wireshark cardio. Getting some reps in. So we have a couple questions in this lab to be able to find out. The first one is saying, what operating system is on the IP address of 10.11.11.94 and what is its device type? So the purpose of this lab is, one, to get some exercise and reps, but also to demonstrate that with network traffic, you can actually find information like that. You can also find out the host logged in as well. You can see the username. Pretty cool. So let's jump into it. So Windows Workstation. We're going to go ahead and we're going to open up the next PCAP inside the traffic. This one is called network traffic analysis.pcap. I'm going to pin that up there. So what operating system is on 10.11.11.94? Find out. And what is its device type? So, we talked about a certain header previously. Let's go and revisit it. There's a certain HTTP header that can provide this information for us. The user agent string. So if we were to go to HTTP and we know the IP we're looking for, so IP.address is equal to 10.11.1.94. Just make sure I got that right. Yep. Wait, 10.11.11? Which 11.11.94. 11.11. So we have a number of requests coming from this source IP now. Perfect. We have HTTP. So let's go ahead and actually follow one of these HTTP streams. No. Here, get requests. Perfect. So here we have SYN, SYNAC, and ACK, but it's still TCP protocol. That's not going to help us. So we actually want this HTTP traffic. So let's follow that. Request is in frame 1192. I think I messed up my filter a little bit. I did, didn't I? HTTP and IP address is 10.11.11.94. Okay, so let's just try to find one of these. Here we go. That's better. Okay, so one of these requests, looks like we had some ones that kind of failed before that, for whatever reason. Here we go. So, source IP 10.11.11.94, making an HTTP GET request to generate 204. And it looks like we had some codes that were sort of pushing us around. We finally got one that worked. So here's a user agent string. Let's go ahead and follow that. And let's do from the IP address. And we can see here now user agent. And this one's a little weird. But this is actually Chrome OS. So we were to do... So user agent belongs to Chrome browser running on Google Chrome OS. Pretty cool. So we can go do like a little lookup if we're not sure. Let's see if we can get all of that. Oh, it's a slow site, huh? It's got to be a better one. User agent lookup. If you're not sure, parse user string. How about this one? Okay, that's way better. I don't know what happened. That site blew up. So Chrome 76 browser on Chrome OS build 12239. Pretty cool what we can extract, right? So that's the first answer to the first question. So let's take a look at another one. What operating system is on 10.11.11.121 and what is its device type? So effectively, we just need to do the same thing, right? No, it's not a trick question over there. So again, HTTP and IP dot address equals this 10.11.11 dot, what was it again? 121. Cool. Let's look for another GET request over here. Looks like we have another one. So let's follow that just to be clear. And if we want, we can actually just copy this right out. It's not Chrome again. I don't think so. Let's copy the value. Copy that value. Let's go back to user agent parse. Nice. So this is actually Chrome browser. This is on version 52. So this is an older one, and it's on Linux. We got Linux over here. Interesting. Yeah. This doesn't sound right though, does it? Am I looking at the right IP address? Yeah. Yeah, 11.121. Cool. So let's look at the next one. Using MAC address for 11. Who is the manufacturer and vendor? Ooh. Well. Copy that. Use the MAC address for 10.11.11.145. Okay. Well, where are MAC addresses? They're in layer 2, right? So IP.source. Let's just look for anything that came from that IP address. And what do we got over here? Source. Motorola. So this is a Motorola device. Do a MAC lookup. Motorola Mobility, a Lenovo company. Details. Cool. So we found the vendor. Motorola is responsible for this one. Cool. See, as you start to kind of do this, it just gets like a little bit easier each time, and that's what Doug and I are saying over there. Like just getting some reps under the belt. That's all what this is about. Let's do one more. So what operating system is on 10.11.11.179? Same kind of thing, right? We'll do one more user agent string lookup. So HTTP and IP dot address equals 10.11.11.179. Let's close up the Ethernet frame. User agent Macintosh. Copy that. Copy the value. Parse it out. So this is actually Safari 13 browser on macOS. Pretty cool. All right, last little bit. See if we can identify what's the next one over here. What version of Windows is being used by the host with the IP 10.11.11.195? Do that once more. Change that around. Getting a couple more reps under the belt, doing some endpoint metadata analysis. User agent, same thing. Copy that. Go over here, parse it out. Edge 44 on Windows 10. Boom. Okay, I think the last one is coming up in time perfectly. So the last one's a little bit more complicated. What is the user account name logged on to the Windows host at 10.11.11.200? That one's a little bit harder. How are we going to find that out? Well, let's pretend all we were able to do was some hunting. So let's do like an IP.source. Let's go see what's coming from this source IP address. So we got some TCP. We actually have this thing called KRB5, like right when we start to search for it. So that's interesting. NetBIOS. See something over here. Gilbert Win7. Look at those. Some authentication protocols happening over here. NetBIOS name service. Queries. What do we got over here? Now, is this providing what we need? It looks like we're seeing Gilbert Workstation. Okay, Boomer. As well, too. NBNS. So we're seeing host name. Like the endpoint host. So a lot of these are authentication protocols. Now, one that we saw earlier on was KRB5. Now, this is another protocol. This is called Kerberos. Quest body. S name string is Gilbert. Getting us close. So what if we were just to search for like KRB5? Not going to work, right? See KRB4, KRB5, RPC. But it's not really helping us for anything KRB. Let's try KRB4. So it's not always going to be as simple as just kind of like putting the protocol. But what if I typed in Kerberos dot? So we could spend all day here if we really wanted. Now what we could do, let's go to Wireshark filters. Gilbert seems legit. Send him an OpenSH question. Yeah. And display filter reference, and let's go to K and Kerberos. And Kerberos, like there's a lot of authentication protocols being used by that IP address. So we're here in this big page. Let's do a Control F, type in name, kind of look through this a little bit, and Kerberos CNAME, client name, CNAME string. And string we talked about before is like, well, it's a string of text, right? So let's go and take a look at this. Let's do Kerberos. Kerberos dot CNAME string. Okay. We give us a lot of information. Let's make sure we have the right IP address and IP dot address. Let's just make sure we're only filtering at least around that IP address. .201 10.11.11 200, sorry, 200. Cool. Take a look at this. We have S name. Do we have any CNAME strings? CNAME. CNAME string. Gilbert Win 7. Go ahead and actually apply that as a column. Brandon Gilbert. So further down in these authentication requests, you see it's a little bit easier when you just apply it as a column, right? Because now we can actually just kind of look at it. Whoops. We can kind of just look at it as a column itself. And instead of going packet by packet, we can just kind of scroll right through. So we're actually able to identify Brandon Gilbert server response to look like. Or rather, just some type of response over here, right? Scrolling right through. CNAME string. Brandon Gilbert. Pretty cool. I think that's a good spot to stop with Wireshark as well. Kind of shows you a little bit of the powerful capabilities of what it can do. If you understand the protocols, then you know what to look for. So we kind of sped it up a little bit there for you, but yeah, take a look. Take a look at that. Everything is recorded in some shape or form. Yeah, applies column is 100% the best. So I want to kind of demonstrate that as well too. I agree with you, Hot Garbage, yeah. Nothing is safe, Pariah. Yes, yeah, I got to go back in, update that Foundry website. It's been deprecated. Cool. I think that's a good spot to stop with Wireshark. We covered a lot of ground today. TCP handshake, TLS handshake, a little bit of a high-level touch base on encryption with the key exchange. We also hopped inside of Wireshark and did a little bit of following protocol analysis. And now we got a little bit more reps under the belt using the filter and just hunting down for protocols, answering questions. So instead of just like randomly doing stuff, now you actually have some targeted questions. We have one more lab to go next Saturday before Doug's going to hop on and give you all a nice surprise. He's cooking something up. But we have one more lab to go on, and we're actually going to be looking at how to extract a Windows executable file from the network traffic and do some inspection on what it was. we're also going to be able to determine whether it was malicious or not. And that's when network traffic analysis starts to get a lot more interesting than just hunting down weird protocols. Pretty cool. That's a wrap for class 11. 11 classes down. Thank you all very much for being here with me. Thank you for spending your Sunday with me on SOC 100 Class 11. Thank you, everyone in the chat. Thanks for the support, as always, being here, the engagement, participation. And we're just starting to get started now on all the fun stuff. So thank you again for being here. Let's keep going one day at a time, and we will get ourselves to Cybersecurity Analyst Tier 1 Triage. Let's just keep going one day at a time. So thank you again. See you in Discord. Have a good rest of the week. And we'll see you next Saturday outside of that. Thank you.